Welcome everybody. So this is the CS292F Statistical Foundation on Reinforcement Learning. Today is our last event of the quarter, and our awesome students, they are going to present their course project that they've spent a lot of effort over the summer. So the purpose of the course is to prepare students for reading machine learning literature and understanding the theory and algorithms of reinforcement learning. And many of the project would be on the topic of reading a particular scientific article in the machine learning literature. So we have 9 presentations lined up, which will each one of them will the ground rule will be 18 minutes presentation plus 4 minutes Q&A. So if you run over, you are eating into your own Q&A time. So everybody could ask a question, but I ask everybody to either type the question into the chat, so the teammates who's not presenting could help answering it to save some time, or to hold your question until the very end, so you can ask them in the 4 minutes that's allocated, right? So I'll be the timekeeper and I'll be tough on you. So the first presentation will be from Ari and Changyuan. And Ari is an undergraduate student, so congratulations for completing the course. So take it away.
Okay.
Hi, this is Changyuan.
Hi, I'm Ari, and today we will be talking about offline reinforcement learning in theory and in practice. So offline learning is about learning from a fixed data set without any further interaction with the environment, and we have many possible approaches. For example, we could use offline learning specific methods like BCQ, one of the ones we will present. We could also use soft policy methods, even though this can be not intuitive, and supervised learning methods like behavioral cloning. And the fundamental problem we face in offline learning is the distributional shift. So if we learn a policy that's very different from the one that generated the data, we may end up in states that weren't visited, and it will be very hard to know how to act there. And so very quickly, I'll go over the distinctions between online reinforcement learning. So we have a policy and we act in the environment with that policy, we update it, and we keep on going with this process. We also have off policy reinforcement learning. So in this case, we have a buffer, and then we take a batch of data from that buffer and use it to update the policy, and then we roll out more in the environment and put it in the buffer. And note how this buffer could even be the same all around our learning. So that's why how we can use soft policy methods in the offline setting, in which we only have a batch of data that was collected once with any policy, and we use that to learn one policy which we would later deploy. So our project is based mainly on 2 papers. First, off policy deep reinforcement learning without exploration, and then probably good batch reinforcement learning without great exploration. And we have worked on both theoretical aspects, providing some important proofs for both papers, and practical elements where we try some experiments in different environments. So we have experimented in 3 different environments: Cartpool, the one we used for the homework; Catch, which is one where you have a falling thing and you just have to move to catch it; and Mountain Car, where you're a car that's on a hill and needs to go up, but it can go up directly, so it needs to balance to go up. And so now I'll give a brief review over each of the methods we experimented with. So deep Q networks are all about learning a function approximation of the Q value function using neural networks. We feed in the states to neural networks, and it outputs a value for each action, which means that this method is only good for the discrete action setting as it is. And the loss function is defined as follows. So we are just trying to minimize this reward minus this Q function. And note how this Q theta prime is different from this Q theta, and that's because it will be better for the convergence properties, and we are updating the Q theta prime to be similar to the Q theta every once in a while, like say every 500 steps. And this here is just any loss function. It could be a mean square error, or it could even be Harvard loss, which is the one we used. So in this figure, we see the difference between Q-learning, the one we use for the homework. So we have a table that has a value for each state and action pair. And in Q-learning, we just have a neural network, right, where we feed in the state and it outputs a Q value for each action. So behavior cloning, it's a very strong baseline for offline learning, and that's why I'll be going over it. And basically, it just tries to imitate the policy that produced the data. So it's a form of imitation learning, and it's supervised learning because we treat the demonstrations as IID state action pairs, and we learn this policy pi theta to minimize the loss function. So as the figure shows, basically our data would be observations or states and actions, and we would be trying to learn this policy where like our data is the states and then our labels would be the actions, and we would try to make this policy very similar to the actions taken in our data. Lastly, we have batch constrained Q-learning. And batch constrained Q-learning is an offline learning method, and it's very intuitive what it tries to achieve. So basically, it tries to minimize the distance of selected actions to the data in the batch. And this also, it tries to lead to states where familiar data can be observed. And finally, it tries to minimize the value function. For our experiments, we actually ended up using a variant of the original BCQ because we worked on discrete action setting environments. And the original one was for continuous action setting. And so the idea is that we learn this GW, which is a state condition model, and that tries to approximate pi b. So essentially what we're using is a sort of behavioral cloning to learn this pi b, and then we are utilizing some threshold tau to eliminate actions. So basically we learn a policy that tries to maximize this Q theta, but only considers those actions that were taken more than a certain threshold. And so the loss function is very, very similar to that of DQN, where the only difference is that we only maximize over certain actions. So that's very intuitive because we don't want to maximize over actions that were taken very few times or almost never, because that could potentially be bad and take us to states we have never seen. So essentially the method tries to address this distributional shift problem that is a very big problem in offline learning. And so for our experiments, each row corresponds to a certain method and each column a certain environment. And I argue that catch is the easiest environment, while mountain car might be the hardest. So for DQN, we can see that it actually was able to learn catch. So even though it's an off-policy method, it was still able to learn in the offline setting in a simple environment. For then, as the difficulty increased, we can see it becomes very unstable. And for mountain car, it's completely unstable. And I argue that it wasn't able to learn that much. Similarly, BCQ was also able to solve catch. It also learned pretty well in cartpole. It was actually achieving like more than 100 steps the pole standing, which is pretty good. That's like almost solving the game. And it also performed very well in mountain car. Lastly, behavioral cloning, which is our supervised learning, performs very well. It solves catch. It also performs really well in cartpole, and it also performs comparably in mountain car, which shows that the data we use for the experiments actually came from good policies, because in fact, using imitation learning, we get very good policies. So that's why behavioral cloning is very important for the offline learning setting. And now I'll stop sharing and Changyuan will continue.
Yeah, so now I would like to talk about why batch constraint is beneficial for the Q-learning. It was from their original paper. They consider tabular setting. They define a macro decision process MB based on the batch by the following definition. So the transition probability is just the empirical transition if it is observed in the batch. Otherwise, they consider a absorbing state and initialize the Q value with the same value. Having defined the MB, this micro-partition process, they can consider the tabular extrapolation error defined to be the true Q function minus Q pi B. And this quantity by Bellman's equation, you can write it in terms of itself, and combining these two together, we will obtain another epsilon MDP again. And using this extrapolation error, we can try to see when will this extrapolation error become 0. And that is the second result. Result 2. So this error will be 0 if and only if Pn and Pb are matched for those S and A visited by the policy pi. So this is very clear from the equation here, because if Pn and Pb are the same, then epsilon is just the matrix P times gamma and times this epsilon. Because gamma times P, this matrix has spectral radius less than 1, so multiplying iterative applying this will converge to 0. So that's why the epsilon is 0.
I have a quick question
hand,
here. So is this the same as the simulation lemma?
Based on the same, just rewrite this as the Bellman equation, right? So it's same idea.
Okay. I think if you move it to the left-hand side and solve the linear system, you recover the simulation lemma.
Oh, really? Maybe, yeah. So this is, it can be viewed as a simulation lemma, maybe. And the other way is, if we have epsilon equals to 0, then because of arbitrary of R, then these two has to be matched. So this is the second result they established. And let's take a look at the condition that this error has to be 0 if and only if Pn has to be Pb. But this Pb is based on empirical transition probability, is usually not the same as Pm, unless we have infinite many samples, or the M has to be deterministic. So they made this very strong assumption that NDP is deterministic. So then this will be 0 if and only if this pi is batch constrained, meaning that the state and action visited by this pi is in the batch. And furthermore, they give the condition that if this SA S prime is in B, then S prime is B. This coherent condition will guarantee the pi is batch constrained, this kind of pi exists. So they have the exploration error 0 when everything is very nice, deterministic, batch constraint, and so on. So putting them together, they have the batch constraint Q-learning simplifying algorithm. So the only difference from Q-learning is that the maximization is taken over A, such that this state action pair is observed in the batch B. So it has the same property as standard Q-learning. It converges, and it converges to, as long as this alpha t satisfies some condition, Parent-Monron condition, so that it converges. So yes, it converges, and it's the optimal batch constraint policy, and no other policy can outperform it in this simple setting. So in this paper, this is very simple tabular setting, and in the deterministic stochastic probability matrix. But if we want to generalize it to non-stochastic and even finite sample or function approximation, we will be in trouble because this doesn't apply. So the other paper we consider is based on 50Q iteration we learned in the last lecture. And 50Q iteration consider a function class F, and then always find minimizing the residual Bellman equation. And here the expectation is taken with respect to the behavioral policy, and it's just the empirical data you have. And every time you have pi k by the usual taking arming. And the result we see in class is, or in the textbook, is this error bound that depends on n and depends on the optimization error. And where we make 3 assumptions: realizability, Bellman completeness, and uniform constructibility. And the first 2 is it can be relaxed and it's pretty making sense, because if the function class is large enough, then it should be Q star should be in the function class. And I want to comment on the third condition, because this quantity is not can be problematic, because d pi h SA over mu SA, it has to be true for S for A and for pi for H. When the behavioral policy is only contains a subset of the entire policy, for example, only the desirable policy, and those weird undesirable policy is not covered, then this mu will be very small for those not covered policy, and this constant will be very large and make this inequality not useful. And also the naive bound of this constant C will be exponential in this edge. So this theoretical, from the theoretical perspective, this is not a really good assumption. And also from the practical point of view, because we have functional approximation, bootstrapping, and of policy learning, we learn about the triad, that the algorithm is not going to be very stable. So some new algorithm and some theoretical guarantee is very necessary here. So the author proposed the filtration, the estimated value estimate, by introducing some filtration function, and they estimate the behavioral distribution and taking the indicator function that this is confident enough. And by multiplying the Q function with the filtration, they can modify the Bellman operator, they can modify the Q iteration and how they obtain the pi. So this approach is taking the S and A such that they have more confidence, and they don't want to take B too large, because that's gonna introduce variance, but B, so it has to be suitable value. With these algorithms, and they change the assumptions because they introduced a new objects. Their assumptions include bounded densities. D pi h has to be less than or equal to U, and this is true for discrete case. For continuous case, is also very mild assumption, and for density estimation error is quite makes sense, because we are estimating mu hat, and we somehow want to control it. For conditions 3 and 4 is similar to the assumption 1 and 2 here, the realizability and Bellman completeness, but just modified so that it works with their zeta filtration function. So this is their error bound they got. Now the constant only depends on U over B, and the rate and the other term, they are comparable to the previous result, but we have a significant less constant C. So in practice, they also compare some numerical experiments with other state-of-art methods and observe very nice results. So that's why what I would like to share with you guys for the second paper. This is the end of our talk, and feel free to ask us any question.
Excellent. So the question answering is now open. We have a couple of minutes. So while people are framing their question, I'll start asking this. So the first algorithm for this offline learning is quite interesting. It doesn't seem to be like running reinforcement learning, but rather just supervised learning. So this algorithm that you guys talk about is called behavioral cloning. You're essentially just imitating what the behavioral policy is doing, right? So could you comment on, like, suppose you already have a behavior policy that is doing that, and you are just copying that. Like, why would you? How could you expect your offline learning algorithm to come up with a policy that's better than your behavioral policy, or is this a slightly different setting where the data is collected not from policies that you can automate somehow with a AI agent?
Right. So yes, you're saying the behavioral cloning is essentially trying to imitate the policy that generated the data, but the data also isn't coming exactly from like an optimal policy. It comes from like the training of a policy, right? So
yeah,
like
let me just shorten my question and say it again. So you already have mu, right? So you already have the behavioral policy. You are using it to collect the data, right? So this is your baseline, right? So if you are trying to imitate the baseline, so what benefit does that give you?
Right. So if you already know the behavioral policy, then there's no point in doing behavioral cloning, I guess.
But in your setting, right? So the behavior policy may not be like it.
Yeah, it's actually unknown.
Okay, I see. So it could be something that's coming from a human operator and doing something that's similar to what humans are able to achieve using an AI. So that's not trivial.
Yeah, exactly.
Okay.
It's unknown. Yeah.
Okay.
Sorry, I didn't answer. Yeah.
All right. Any question from other folks? Okay, so maybe I'll ask the second question about the BCQ. So this is called a batch constrained Q learning, right? So the key step of this BCQ is this thresholding rule, right? So you are selecting a set of actions and end states based on the number of times you visit those actions and states, right? So what is the intuition behind this thresholding rule on a very high level? So why are you not using those data points where you have observed only like a few times, but rather having to ensure that it is larger than tau, the number of times of state action visitation?
Right. Yeah. So I think the intuition behind the threshold is that if you end up selecting actions that were taking a lot by the behavioral policy, you're kind of staying close to the behavioral policy. So you're trying to solve the distributional shift by staying close, but still maximizing over other actions. But I think the intuition is that it helps you stay close to the behavioral policy.
Okay, that makes sense. Changyuan, is there a theoretical answer to this question?
Yeah, it's similar to the other paper they proposed, density one. They also have the similar idea to be more confident. Then they would take this action. Otherwise, if it's not supported by the data, then this could be just noise or.
Excellent. Yeah. These are very similar ideas to things that we covered in the class related to the fictitious estimator and also the pessimism idea that you guys have explored in absorbing MDP, right? So if in absorbing MDP you're setting it to be 0 rather than 1, then you are getting pessimism rather than optimism, right? So which are like things that you want to optimize your policy based on the changes that are supported by the already collected data. Yeah, thank you very much. So we don't have more time, so let's move on to the next talk. Yeah, for more questions, yeah, you can ask the team in the chat messages, and they will respond asynchronously.
Okay. I will share my screen, and my talk will be kind of informal. And I will be talking about optimized Turing query using deep reinforcement learning. So first, let's talk about query optimization. So we want to transform the SQL, which is a declarative language, into query points, right? So here's a query optimizer. And it is crucial for database performance, where a good query optimizer can speed up query execution by orders of magnitude. And the problem itself is very complex. It has been a hot area of research for decades already, and we still have some issues with string query. So in 2002, a commercial quality database query optimizer required 50 years of power of development. And just know the join order problem is NP-hard. So let's give a high-level view of this query optimizer. Like the classical query optimizer contains 3 components. You have a cardinality estimation, where you want to estimate the number of tuples using statistic, distribution, correlation, joint relation, those sort of statistical plans. We also have a cost model. It will be a complex function that maps space cardinality into the cost. And at the end, we have plan enumeration, where we want to explore the space of semantically equivalent join order to find the plan with a minimal cost. And at the end, we output the suboptimal query. So there's a lot of recent efforts in database community to use learning-based algorithms to tackle the query optimization problem. So for example, there are learn cardinality estimations, neurocard, deep unsupervised cardinality estimation. There also works on learned cost models published on Signal. And I will be talking about learned join order plan. So I will be, especially I will be talking about these 2 papers, learning to optimize join query with deep reinforcement learning, and join query optimization with deep reinforcement learning algorithms. So due to the time constraint, I will not be talking about NEO, but NEO is also a very good paper. I introduced a new architecture for the deep learning network. Right, so we will be discussing these 2 papers. The goal is that we want to leverage reinforcement learning techniques to find a near optimal query plan that minimize the natural join cost and time. So just some background information. Let's say we want to join ABC 3 relationships. No, the inner join is associative and cumulative, meaning we could change the order of this plan. So all of these 3 are semantically equivalent, meaning the output will be the same. So the question becomes which of the above plan yield the most cheapest query plan, right? So traditionally we leverage the cost model and cardinality estimation to find the suboptimal query plan. Also note, for join queries, we also have three kind of operations that we can perform. We can either do nested loop join, meaning we just have 2 for loops that, for example, is join on identification, then we find the matching records. Or we can use hash join, meaning we can generate a hash table on one relation and then scan the other to find all matching tuples. We can also do sort merge join, where we sort 2 relationships and do join. Right, so we can see if the table is quite small, the nested loop will actually be better. But if if we already have a hash table for some relationships, then maybe hash join is more preferable, because maybe we don't need to regenerate the hash table. We can use the previous one. So the first paper I will be talking about, I would say, is a pioneer paper that published on 2018 on learning to optimize join query with deep reinforcement learning mainly from Yu-Xiang and UC Berkeley group. So let's connect the bottom up join enumeration with MDP, right? So query graph, each vertex is a join relation R, and each vertex is join predicate between 2 vertices. So essentially, where the state will be the graph itself. A join is merged 2 connected vertices into 1 vertex and links the union of the edges from the 2 vertices. So after we join 2 relationships, we have to relink the edges. So as you can see, the graph is a state. C is a join action. and we can make the negative, we can make the cost negative such that we want to maximize the reward. So over the definition, here's the minimize because this J is always non-negative. So the idea is we want to perform a series of a sequence of actions such that we minimize the total cost. And at the end, the ending graph is a single vertex. So some high-level intuition of this, like how heuristic query optimizer might solve the problem is that here's an example of the greedy operator, where you can always select the lowest cost join for each state. But the problem with this approach, although simple, is we might not consider the future rewards. We always try to find the current, the minimum cost of current state, but we might lose some opportunities in the long run. So the idea is that we want to try to find the suboptimal policy based on small number of samples with online reinforcement learning. So here's basically the V function and the Q function rewritten using G and C, which is the state, the graph, and an action. So first, the paper collected offline training data. So they collected graph, join, graph prime. So this graph is the initial, like the previous state. Graph prime is the state after the join operation, and then the cost. So the cost is coming from the cost model. So note one single query plan contains many training data, sub-query plans, right? So like the end goal is that we want to transform the entire abstract syntax tree to a single node. So along the way, we can generate a different graph and graph. So so the author argued that the heuristic query optimizer plan might actually be too good because it's already being optimized significant amount of time, right? So like the Postgres or like Oracle optimizer are already very good. So the author added noise to encourage more exploration. So we can think about it like you add the epsilon greedy to explore random decisions. And then how do we transform the feature of this this join into like how do we do feature selections, right? So how do we represent the participating relations and fields with into the machine learning inputs? So the author decided to use one-hot encoding, where as you can see from the bottom graph, if you want to select a star from these three tables, we'll just put all the fields and all the necessary information into one vector, and we will say 1 is the one we already have, and 0 is if we don't have. At the end, everything will become 1. Note if so, this is a simple query, but in real life, we might we might have greater or less or range queries, right? So like we have to reflect the selectivity. So meaning we can use like quantile sketch to estimate what's the selectivity. So for example, if you know the range is from 1 to 1,000, and if you have an assumption on the it is a uniform distributed table, then you could say you could modify the selectivity to like 0.8. At the end, there will also be 2 additional bits to represent hash join and index join. So in the paper itself, it only consider hash join and the index join. It didn't consider sort merge join. So the model they use is a deep learning network. So the idea is that neural network seems to be good to function approximator for nonlinear function, right? So this this model itself is pretty much nonlinear itself. Multi-layer perceptual neural network to represent the Q function, and the paper had a constraint on the training time, so they decided that they want to use 2-layer MLP which yield modest training time, less than 10 minutes, and gives the best performance. Where Q-learning is trying to maximize the expected rewards of an action in a given state. So at the end, we want to find a policy that maximize the expected value of the total reward. So just remember the reward itself is -1 times the cost. Therefore, we want to maximize it. So the deep Q network is trained on the offline dataset, where the cost is approximate using the cost model, right? But the cost model may fail to correlate with the real world. It often underestimates the cardinality, or often the function itself is inaccurate. So therefore, we want to retrain on real execution running times of the cost model. So when we, after the pre-training step, which converts to the sample from the heuristic optimizer, it fine-tunes the network using the real execution time. So here is some evaluation result, as you can see over the right. I would say the lower is the better. So as you can see that for the execution latency for large queries or complex queries, the deep Q learning is actually achieving some good results, or especially over here. And another matrix is on the optimization latency, where you can see for simple queries, because it is using neural network, it spend more time on computation, I guess the weight. But as the query become more and more complex, using the Q network give you a better result. At the end, it was said that in average, the deep Q learning execution latency is 14% better. Also, one of the intuition of using this Q learning is that at the end we have a bunch of scores, right? So like instead of finding the optimal, we can also find the top K query points. So this is sort of motivating the second paper, which is built on the previous paper that I talked about. It's called Joint Query Optimization with Deep Reinforcement Learning, published in 2019. The goal is that they introduce fully observed, sorry, I forgot this stand for. FOOP, which allows query optimization as fully observable reinforcement learning problem. So they want to answer these two questions, mainly. How effective are Q-learning and policy gradient-based reinforcement learning approach for query optimization? Which of this approach shows the best performance? So let's first talk about this futurization. So similarly to the previous paper, which using like one-hot encoding, it is using a matrix instead of the vector itself. So here's the DQ that we just talked about, and here's their proposed features. So let's say so right now it's joining four relationships. Therefore, it has it will be 4 by the number of fields, the summation of the number of fields matrix. The idea is that agent now knows that at any state which subqueries still have to be joined to reach a terminal state. And also the agent can see which subqueries were already joined in the past. So that's why it is fully observed. Right, so they also did a transformation of the cost estimation. So previously it was -1 times the cost, where they modified it using a square root. I think the intuition was that there are only a few good plans. So in general, the costs are very high. Which if it's very high, then you can see that it will be -10 to the 6, -10 to the 16, which is very large. So they decided to map it into 0 to -10. using this equation. So the upper bound will be 10 to the 16 in this instance. They also introduced a new idea of ensemble learning. So that's why I talked about this top K curve plan previously, right? So like the idea is that we can train a lot of learned policy from different training. Learned policy from different training may have divergence, resulting in different optimal curve plans for the same curve. So essentially you can train in this graph you can train 4 different policies on the same training data set. The agent can ask for third or second opinion before taking action. So in the paper itself, the author had 5 different learned policy from the deep reinforcement learning. And then because you can have the top K curve plans, you can find you can basically score in them and then find the one that all policy agrees. So in the paper itself, it compare and contrast between 3 algorithms: deep Q network, double deep Q network, and proximal policy optimization. So Q learning involves bootstrapping such that overestimation can be problematic. Therefore, double deep Q network try to solve this overestimation problem by using 2 value function, and then use one to determine the grid policy, while the other one to determine the value. And they also introduced this proximal policy optimization, which is a policy gradient descent gradient method that allows the policy ratio to stay in between 1 minus epsilon and 1 plus epsilon to achieve better convergence and lower empirical complexity. So here's some evaluation result from the paper, where they essentially found that proximal optimization is always preferred, and by using ensemble learning, they can decrease on the variance, I think. Right. So the result demonstrate that ensemble learning significantly improves the overall performance of the reinforcement. So far, from all the paper I have read so far, all the reinforcement learning algorithm in query optimization problem leverage model-free algorithms. So it would be natural to ask the question, how about model-based algorithms, right? So it's we know model-based algorithms are more simple efficient, and it's probably more robust for different query tasks, right? Because we are building a world view rather than using this case-by-case analysis. So on another high-level intuition is that it might have high potential for better integration into the database context, right? So like model-based reinforcement learning learn a simplified model of the environment and lets the agent to predict the outcome of potential action sequence, leverage the model to act. Whereas the classical solution for query optimization relied on dynamic programming or greedy algorithms and cost model and cardinality estimation to estimate plan costs and try to find the query plans, where essentially they are also trying to model the database in the database context. So just like how neural network try to imitate the brain, maybe model-based is a better approach for database query optimization. So the goal for future work is so I would like to try apply expert iteration algorithm into query optimization problem. So this algorithm is from the paper of Thinking Fast and Slow with Deep Learning and Tree Search from Google and UCL. The high-level intuition would be we want to imitate the behavior of expert, which already have the query optimizer, and then we can iteratively increase the performance. So just a brief note on this algorithm itself. The idea is that you have apprentice and expert. The apprentice is implemented using deep neural network. We train apprentice on learning target generated from the expert's imitation learning. So essentially, the idea is that we want to build some intuition And then we have an expert implemented as tree search algorithm. And Mini is about reason, which is quite slow because it's a tree search algorithm. The expert can be calculated from labeled training data. And then we use a new apprentice to add this expert. Provide access to strong policy for bootstrapping. Here's the algorithm itself, where you have you are generating the just like imagination from the apprentice, and then you improve the expert based on the apprentice itself. Right. So that's all I have to talk for today. Thanks for listening.
Thank you, Fuheng. Yeah, I wanted to cut you off early. Now you have exactly 1 minute for question and answering. So I'll just quickly start with a few clarification questions. So first of all, is the transition dynamics known in your problem? And is it deterministic or stochastic?
Wait, this question is kind of hard. I would say deterministic, but
okay, but you're not using a model-based approach, so therefore you don't have to model it. But it is deterministic and probably known, right?
Yes.
Okay. So the second question is the immediate reward known, right? So are these cost functions,
yes,
like from your model, immediate reward or future reward?
Immediate reward.
Okay, so they're known and they're some kind of parametric.
They are estimated.
Okay. And your approach seems to be offline. So were there previous methods that uses online reinforcement learning for addressing the same problem? Does it improve?
So they were targeted for online learning, but what they found was that it didn't work. Well, it didn't work well because they explore different ideas, and then it takes too much time for the algorithm to finish the query itself. Like one researcher said, they spent a year. They spent 6 months running the.
So it's not learning.
Yeah, exactly. It's not learning.
Yeah. So maybe some kind of hybrid online offline approach could work better. Right. So the last thing is that this ensemble idea seems very interesting. So one idea is that you can add an additional multi-arm bandit onto that, so that you have some performance guarantees in terms of the regret of with respect to the best performing like arm in hindsight. Okay, so currently it looks like you're just using majority voting approaches.
Right, exactly. That's what they said in the paper.
yeah, very interesting talk. All right, so let's move to the next talk by Yichen, Mengye, and Ming.
Yeah, hello guys. Let me share the slides. So hello, I'm Yichen. Our team also includes Mengye and Ming. We are all from P-Stat department. So our project is about the paper called Probably Efficient Q-Learning with Low Switching Cost. And in the overview, I will be responsible for give you introduction, problem setup, and algorithms. And then Mengye will discuss some lemmas as preparations for the mean theorem. And Ming will show you the mean theorem with its proofs. So this paper is about reinforcement learning under limited adaptivity or low switching costs. It refers to the setting where the agent is allowed to act in the environment for a long period, but is constrained to switch its policy for at most n times. So there will be a small switching cost to restrict the agent from frequently adjusting the strategies. And there are strong practical motivations for developing algorithms under limited adaptivity. For example, in medical applications where actions correspond to the treatments, it's unrealistic to execute full adaptive algorithms. And what happens in reality is that one can only run a fixed policy approved by the experts to collect data. And a separate approval process is required every time if somebody would like to switch to a new policy. And in personalized recommendation, like online video recommendations, it's impractical to adjust the policy online based on instantaneous data, since there might be millions of feedbacks from users. And in reinforcement learning guided new material discovery, it also takes time to fabricate the materials and set up the experiment. Okay, and a common practice is to aggregate data in a long period before deploying a new policy. And in our presentation, we will introduce an algorithm called Q-learning with UCB2 exploration and show you the proofs of mean theorems about the regret bound and the local switching cost bound. So the paper used the notations which are quite similar as what we use in the lectures. So I will skip the introduction about all the basic notations. Just mention we use this PV and P hat V to show the expected value of value function and the observed value function. So in the regret, we assume K is the total number of episodes, and the regret is defined by the sum of the over all the episodes, the sum of the difference between the optimal V and the V pi K. Here, pi K is a policy adopted before episode K, and the V star is the optimal value function over the entire episode. And the one thing I need to emphasize is the local switching cost, which is used in this paper to quantify the adaptivity of reinforcement learning algorithms. So the local switching cost denoted by a capital N switch is given by the sum of the N switch, where this N switch are the switching cost between the pair of policies pi tilde, defined as the number of each X pairs on which the policies are different. So the definition for N switch is given here. And then this capital N switch is measuring the change of the entire episode between every neighboring episodes. So there, by the definition, there is a trivial bound for it, which is bounded by HS times K minus 1, just obvious from the definition. Then before I show the algorithm, here are some preparations about some functions and new estimates. So this floor function gives the function tau r, and we use tau r to define something called triggering sequence. So in the triggering sequence, the eta and r star are given, and this sequence for time consists of two parts. The first set are the consecutive numbers from 1 to tau r star. And in this set, it's just taking the values by the tau functions. And the difference between the two sets is that in the second part, there might be integers between every two tau values. So they're not consecutive. Then this tau last t is defined as the maximum integer less or equal to t. And we have some function defined by as alpha t. And there are two estimates in the algorithm. The Q tilde is called the running estimate, which is updated after every episode. And Q is our delayed estimate, which is only updated occasionally, but used to select the action. And about the two estimates with the triggering sequence, we have the following two-stage switching strategy. So it says given the state action pairs for the t time, and by observing something, we will get the running estimate Q tilde. But whether to update the policy network Q is decided by the two stage. Stage 1, if t is less than tau r star, then we always update Q according to Q tilde. And when t is greater than tau r star, then we only update when the t is in the triggering sequence. So which means in stage 2, we don't update every step, just when t is in the triggering sequence, we take the action. So then we have this algorithm. We initialize these parameters, and for every episode during each step, we take the action, and we here we use the Hofstee type bonus, and we're going to discuss based on this bonus. And then we update Q tilde of the running estimate for Q, and the V is given here. So the key step is here. If T is in the triggering sequence, then we update the policy. Otherwise, even we have the running estimate, we don't update to Q otherwise. So Yeah, and I'm sorry, I need to introduce another page of the notations. In the discussions later, you will see the alpha T0 functions, alpha Ti functions. They are defined like this, and they have some very nice properties by the lemmas. And then we define the delta tilde k and the phi tilde k as the errors of the estimated v tilde relative to y v pi k and v star. So a very trivial result here says the regret bound defined by this sum is less or equal to this. We replace the v star by the vk, and then we will it can be written by this sum of delta tilde k. And then in the next lemmas and proofs, one of the goal is to relate this quantity to this quantity to help us bound the regret. So that's it, and I will pass the control to my team member Meng Yi.
Hi guys, give me just 1 second to share my screen. Okay, let me see, can you see my screen now? You can, right?
Yes.
The preparations. Okay, so for my part, I will introduce some lemmas to get you fully prepared to go through the main theorem. For the main theorem, we want to prove the regret bound and the switch bound. So the first one, as Yu-Xiang said, we just rewrite our regret function as the summation of the delta tilde. So the first lemma here, actually, author shows like if for each delta tilde, it can be bounded by two parts related to Q tilde. The first part here, this one, it called main part. And the second part here, we call it perturbation terms. So to prove this lemma is kind of, it has two parts. Firstly, we just use the definition of pi k to convert this delta tilde to v tilde, and then it will convert to prove this inequality, this inequality. Then actually we just prove it by two steps. One is this v tilde is smaller than the first term, and then the v tilde is also smaller than the second term. So for the first term is obvious, and for the second, this k prime term, k prime here is the tau last plus 1, and then like to prove the second, to prove it's smaller or equal to the second term, we just introduce the two new vector q old and q new, it defined as the q tilde k prime and the q tilde k. And the difference between these two vectors is only one component, which is the only action we taken actually. So if the q new is also maximized at AHK, then we will have this inequality. But if it's maximized as other component, then we will have the v tilde smaller or equal to the k prime part. So then combined with the first inequality, we can get a proof of the first lemma, which actually is split the delta tilde into two parts, the main term and the perturbation term. And then the second lemma for us is to get the bound of the perturbation term. So basically it's bound by beta is something related to alpha IT and also I guess BI in the algorithm in the steps. And then for this proof, there are two things I think very important. One thing is we observe it's a good property for alpha IT, the summation equals to I. So so we can rewrite this equation actually is just the iteration from the algorithm. We just like apply each step into the update function, and then we can get this equation. When we apply this good property of alpha IT, then we can rewrite this equation into a difference. And another important thing I think for the proof here is author found this term to bound DI. This term is a martingale. Then we can apply Azuma-Houghton inequality to bound this term. Then and then then apply Azuma-Houghton inequality, and also the property of the I guess there is a bound for summation summation alpha IT square. So also apply that one. We can get the final result here. And this lemma actually tells us we can bound the perturbation part by these three terms. And then the last lemma here is another preparation for the main theorem. We will use it just in one step. It gives us the bound for the error accumulation under delay update. And I will not go through the proof about this lemma. If you have questions or you are interested in this, we can discuss in Q&A session. Okay, then now I think you're ready for the main theorem proof. I will pass to my teammate, Ming.
Hello everyone. So now I'm going to state the main theorem. So actually, this is only one part of the paper. So the paper has another theorem called Q learning with CCB2B, with the Bernstein type bonus. But that the idea of the proof is quite similar. So, and also due to the time limit, we just show this one. So it says that by the previously mentioned algorithm, if we choose the eta to be this and r star to be this, we can have the required bounds. We can have this required bounds, and the local switching cost is bounded by this term. So so the proof of this theorem should be divided into two parts. First part is to show the bound for regress. Second part is the bound for the switching cost. So let's look at the first one. This is by the previous lemma, and we take care of this part and this part individually. So this part has been this called its perturbation part, and this part has been bounded in the previous lemma. And this we first take care of this one. So let's first consider q star minus q pi k, and by the definition of the q value function, and also we plus minus some terms, and we collect collect some of them, and we can get this result where the ck is defined in this way. So now this q tilde k prime minus q pi k can be written as q tilde k prime minus q star plus q star minus the q pi k. So as we can see here, and then the first term, so this term is given in one of the lemma. I think we didn't show that, but this is given the one of the lemma in the paper, and this part is here. So so notice that this alpha 0 tau plus t, this term will equal to 1. Oh yeah, I think I should mention this later. Yeah, I'm sorry. So the beta. So look at this term, beta tau plus t. So this beta is given by this function. Beta t is equal to 2 times the sum of alpha ti times bi, and this sum is equal to of order square root of h to the power 3 times I over t. So so where I is a log factor, and by the lemma 2, the perturbation bar is given by this. So now we can combine this and this together. So notice that the tau plus t is the is the time in the triggering sequence which is less than t. So this beta tau last t is less than this beta t. So as we can see, it's less than this beta t times the factor, as we can see here. And also this term is the Kasi k is a zeta term, which is introduced by Mengye, and which means that we can combine this term and this term and this term together into a bt times a constant c prime. So then we have this. So finally we have a bound for this delta tilde k, and we have the first term and the second term. So we look at we are going to sum over k for this bound. And the first term, we have a coefficient alpha 0 tau loss t. So notice that this guy is equal to 1 only when the tau loss t equal to 0, which means that which happens only t equal to 0. So then the sum over k is upper bounded by this SAH. This condition is given under a proper initialization of the Q function and V function. So although in the paper the how to initialize the V is not clearly specified, but I guess it might be zero to as the initialization for the V value function. Okay, and for the second term here, so we notice that it
should be the largest possible value for
largest possible value h.
Right.
Yeah, but I guess under that scheme, it may not be explore every state in the first SAH steps.
Yeah, I see. We'll talk about that technicality offline.
Okay, thank you. So for the second term, we see that for the inner sum, there's a phi tilde ki and a phi tilde ki in both terms. So the summation is sum over I. So if we change the order, we can take this out. So that's what we have done here. So then we can take this out, and this sum is bounded by 1 plus 3 over h in the lemma 3, and so we also bounded the second term, and so for the rest term we can apply the similar proof as in the reference, which is given in the end. So we can obtain a propagation of error equality and deduce that the target is bounded by this. This is also the same bound as in this paper. Okay, and so the second part is of the switching cost. So the switching cost is less than tau r star plus RA minus R star, where RA is the final index of updating Q such that it satisfies this condition. So actually, I think this H is redundant, but the reason is that RA is less than the final update of the Q tutor, and we are only updating everything at most k times. So the sum should be less than k. I think the k is enough. Yeah, but the result does not change. And by Yu-Xiang equality, the sum of RA is bounded by this factor, and so we are going to sum over all A, and so we have this bound, and we are going to change its tau r star by the definition of this tau function, and we have this factor, and due to the definition of R star, this guy is equal to 10h squared times A, and so the whole thing is bounded by order of h squared times A times the log factor, and we because this is the first single H and S, so we're going to we multiply this term by HS, and we got this result. So actually, I have one question in this paper. I've spent a lot of time to think about it, and I didn't figure it out. I don't know why the R star here is. So actually, the R star I think is the reason choose R star and eta is from this lemma, but in the proof of this lemma, the only requirement to eta is that eta should be less than 1/2, and I don't think the value for R star is kind of comes from nowhere. I didn't figure out if anyone know why the R star has to be this and eta to be this. Maybe you can tell me, and I'm very happy to know that. But given that if the R star, so as I said, the only requirement for eta is that eta is less than 1/2. So if we can improve this eta to something like this, where fh is a function on h, and this is non-negative, so we satisfy the requirement for eta, such that eta is less than 1/2. and R star is chosen like this, then we can improve this switching cost to the factor, to this factor. And this looks very reasonable to me because that we know that the trivial bound for the switching cost is h times k minus 1 times s, and that will be linear in h. So we take in the condition of the action space, and we reduce the cost from the k. So it seems like we consider something, and this we reduce the cost in k, and we take some compensation, which is taking into consider the a. But the bound in the paper, it also increased the order of h. So this looks quite kind of like there's some space to be improved. So we can do this by a factor of fh. This, for example, if we take this f to be a log function, this looks quite reasonable to me. And I'm not sure. Also, the question is on the eta and the r star. So I'm hoping if someone can answer this question, I will be very happy to know that. And this is a reference I just mentioned in the proof. And so this is all of the presentation today. And thank you for listening.
Yeah, excellent presentation. So the paper that you're actually covering is missing, but yeah, this one is the paper that you're covering is based on the technique initially developed in Jing et al. Yeah. So I have actually a couple of questions, but we don't have time to go over all of them. I can send you some of the questions offline. But first of all, like the switching cost is defined to be the number of changes in the policies, right? So
yes, that's right.
So the question is that are the paper only using deterministic policies, or do they also allow stochastic policies?
They only consider the deterministic policy. The reason is that they argue that it is without loss of generality, because we know that there's a stationary. We know that there's a deterministic optimal policy. I also want to mention something about that. So in the proof of the local switching cost, it seems that we can sum for this. We can also sum over S, and then we can apply. We can by the Yu-Xiang inequality, we can get something here by S. Here we have one more S, and we have log K over S by S times A. And then finally, everything is the same, but the only change is that in the log factor, we got log K over S times A. And to me, I think if I'm going to prove this, I'm adapt that approach and to get a slightly better bound. But I think the other use this scheme is kind of like a law. It kind of also can be used to the case that you have the stochastic.
Yeah, there are some slackness in the analysis, obviously. So the lower bound of the switching cost is HSA, and the upper bound is H cube SA log K, right? So your improvement is very plausible that you could get it down to HSA log K. And if you further allow stochastic policy, as we have seen in the second homework,
yes.
with a policy action army elimination algorithm, so that would potentially allow you to get rid of that log K as well. So for optimistic policy, dependence on K cannot be removed. There's a lower bound. I think there's an iterated logarithmic factor in K from even the multi-arm bandit literature. But if you allow stochastic policies, then this almost trivial policy arm elimination algorithm would allow you to improve the switching costs into something that's completely independent to the time horizon, right? I think there might be a paper to be written here.
Okay.
Yeah, thank you for the presentation. Now we are a few minutes over time. Let's move on to the next presentation. And Avinash is going to tell us about radio network design with reinforcement learning.
Hey, let me start. Oops, I don't know. Oops, I somehow can't share the screen. Okay, now I can do it. All right, so I hope everyone can see this and hear me all right. Am I audible?
Yes, I can hear you well.
Okay, thanks. So yeah, I'll be discussing mostly application of reinforcement learning in the context of digital communication or radio design. I am a first year EC PhD student who works in sort of wireless communication, sensing for wireless. So this is sort of closely related to my research area. So why is this needed? So you might ask, like, like there's already 5G, things are already, progressing well on the communication domain. Why is there a necessity to sort of incorporate more like learning, which might make things a bit less interpretable and so on. So what we have to keep in mind is all the components in the current radio, the OSI stack, are all sort of strictly co-designed. So for a given transmitter, there's sort of a fixed receiver and so on. What this does is, even though it improves efficiency and so on, it like sort of introduces a very sort of a rigid standardization procedure where things will work only with if it's paired with the corresponding thing. So that will introduce some sort of restrictions in the spectrum which we can use and so on. So you might have heard about like companies asking for more bandwidth in the spectrum, and that being regulated by the US government and so on. So it's a very sort of an expensive thing, the spectrum. So around 2016, DARPA started this challenge called the Spectrum Collaboration Challenge, where they wanted to promote more research into developing more flexible radios, which could sort of switch between using different parts of the spectrum and so on. And the natural thing was obviously to move to data-driven techniques. And while there are many parallels between these classical signal processing blocks, which are used in these low levels of the OSI stack, and the machine learning tools. So for example, an FIR filter, if someone has done like ECE, is very similar to the convolution layers which we see. The recurrent neural networks for machine learning is very close to the IIR filters we use. So there is definitely some, like it's worthwhile investigating all of the advances, or like basically applying the ML algorithms to new areas, including wireless communication. So in this project, I explore basically using reinforcement learning to learn a few things which are part of a communication link. So just to give a simple overview, 101. So what is our goal? It's to sort of transmit information from input to outputs, or transmitter to receiver. And usually this goes through a channel, which will introduce certain, you can say, errors in the message you're transmitting. This could be in terms of like adding noise, it could be delaying the signal, it could be introducing echoes and so on. So at the transmitter, we take the message signal, we modulate it, we modulate a carrier using this, so that you can transmit it on a physical, using a physical device on a channel. So the channel could be anything like a fiber optic cable, just open air, what you have it. And then the receiver just like receives something, does some post processing, and then hopes to like basically decode the message and go from there, and like basically use that information. So what is modulation exactly? So you have some message signal, and you can think of it to be a sum of some in-phase and quadrature components. And like, I'm not going into too much detail here. If anyone has questions, you can ask me later. But what X of t is used to modulate this carrier, which is usually a continuous wave, a continuous sinusoid. And in digital communication or modulation, what we do is we restrict this X of t to be a certain set of values. And those values are sort of depicted in these constellation diagrams. So for example, let's say you have a bit string, which consists of like, let's say 0 1s. You can use 2 bits to create a symbol. And basically that is used to then modulate a carrier. So that is what the QPSK modulation scheme does, which is called quaternary phase shift keying. And there are other modulation schemes which used like 4 bits and so on. So what this does is, and like basically these constellation diagrams are the maximum valid values which we allow, or the alphabet which we have, sort of governs the modulation scheme which we are using. So one thing we can notice is, like, when you're sending less number of bits, that means you have to send more symbols. So you're spectrally not efficient. So bandwidth wise, you're not efficient, but decoding or basically post processing this at the receiver side makes simple, and there's a lot of room for error. While if you have things which are more spectrally efficient, for example, the 16 quadrature amplitude modulation just shown on the right, you can pack more information in the same amount of bandwidth, but then there is just prone to more errors because there is lesser sort of like, you can see the symbols are all very close to each other. This will become evident when we explain about the demodulation. So like think about demodulation as just like you can think of it as like a K and N sort of a thing, right? Like, so you receive some symbols. So the X marks here are basically what you transmit. The channel will impose some noise, some basically imperfections on it, and that will get scattered all around. And then you have to make a decision at the receiver, and then you can use a simple like metric or like a algorithm, which is the minimum distance decoding. So you take some received symbol, you check, okay, what is it closest to, and then you assign that as the received symbol. So from this, it's evident that if you use something like a 16-com, it's harder to have less errors because everything is so close by. So there is less room for error. While with QPSK, it's like sort of easy. There is more room for error and you can manage. So this is just basic 101 to this thing. So what did I do in this project? So my goal was to like say, okay, I will not impose any modulation demodulation scheme. And then let's say we have two agents. One is a transmitter, one is a receiver. And if they were just allowed to communicate through an environment, which is our channel here, what would they learn? Like, how will they figure out what is the best way to communicate between each other while maintaining a certain set of you can say restrictions, which I will explain. So initially what I did was to make the problem simpler. I fixed the receiver. I said the receiver is going to do a minimum distance decoding based on the QPSK. Let's see if the transmitter can figure out what it is supposed to transmit to ensure a good quality transmission. So what is good quality transmission is basically is assessed by the bit error rate. How many bits are erroneous given sort of the noise in the channel and so on. So here's my problem setup. The transmitter is given a bunch of random strings of a fixed length. So I set the bits to be 2 so basically working with QPSK. And then these symbols are modulated. So the transmitter modulates the symbols or generates the symbols, which is sent through an AWGN channel, an additive white Gaussian noise channel. This is our environment essentially. And the receiver receives this signal and then it demodulates it. And then what we can do is we can basically check what's the error between what we have sent and what the receiver is received. And then based on that, the transmitter receives a reward. So it gets a loss signal essentially. So what the transmitter is essentially trying to do is to learn a policy. So to like sort of draw parallels to our reinforcement learning terminology, it's trying to learn a stochastic policy whereby which it can maximize the expected reward. And then the environment is essentially the AWGN channel I mentioned. So we can basically use policy gradient, compute the estimate of the gradient using the score function trick, which is sort of popular, the log trick, and then update the parameters of the transmitter to improve the reward and hence the transmission quality. So this is just like a quick revision of what we did in class. So there are multiple policy gradient algorithms. I did something with reinforce algorithm. I tried doing actor critic, but the results weren't so great. I'll mention that when I explain the results. So with this, what we have is that what I did was I used a simple neural network with a single hidden layer in the transmitter. And then each input to this is a single bit string, which is of a fixed length. And then the output is like a Gaussian policy is what I was trying to learn. So I was trying to predict what the means would be. I also tried doing something where I parameterized the standard deviation as well, but that didn't turn out so great. So I stuck with just parameterizing the mean. And then the transmitter output is basically drawn from the complex normal distribution, which is parameterized by the mean, and I had a standard deviation. And then it receives a loss signal from the environment, which is given as basically the L1 norm between what the bit string I sent and what the receiver decoded. And I also introduced this additional constraint, which is like, you can say, a regularization term. So this is to prevent the transmitter from just separating out the symbols by putting a large distance between them. So if you go back to the constellation diagram, we can always see that if the symbols were farther apart, then doing a minimum distance decoding is much simpler. But what this translates to in like actual radio is like the transmitter is using a lot more power than you can sort of use, like, or you want to use. So by simply boosting the transmitter power, we can hope to obviously do better, but then that's not an ideal scenario. So I've introduced this term to sort of restrict the energy being of each of the symbols. So I basically use the negative loss as the advantage estimator, and then use vanilla policy gradient, or like basically train it in an actor critic setting. So in this case, what I do is there is no temporal structure to any of this, because these bit strings could be random. So there is no real state for my transmitter. So the episode length is just like effectively 1. So it just takes a bit string, it sends something, it receives a reward based on the transmission. And then, like I said, the action space is like all over the complex plane. It could just be like you're just sampling from a Gaussian distribution. And the gradient is basically working out from the score function trick. We can obtain this. So I trained this transmitter for like 600 iterations with 500 steps in each iteration, and then use some Adam optimizer. To assess the performance of the agent, I compared the bit error rate it achieves with the theoretical bit error rate of the QPSK modulation scheme. I also looked into see what the learned constellation looks like, and how much more energy, or what's the average energy per symbol the network learns. To keep in mind that the average energy per symbol, the ideal average energy per symbol is just 1. So coming to the results of this, with the actor critic, there is like initially my plan was to just impose, or like basically artificially create a temporal structure in my problem by introducing multiple bit strings and so on, and then basically use a critic to estimate the value and so on. But that didn't turn out so well. The training was very unstable. I used to like get constellations used to just blow up and get like symbols all over the place. So I quickly abandoned this approach and then went back to the reinforce algorithm. So I ended up with this. So the orange line there shows the theoretical BR, or the expected bit error rate, and the blue line is generated from the learned agent. So just to analyze this, so the x-axis here is something called as the normalized SNR. So it basically tells you what the quality of the channel is. So as expected, if the quality of the channel is really bad, so there is a lot more noise, then we experience more bit errors. While as opposed to when the channel is really clean, so the SNR ratio is very high. And this is normalized for the average symbol energy. So you can't just simply say that I will put more energy and get lesser errors eventually. So we see that the reward sort of becomes constant after a few iterations. But what you have to keep in mind is we are also interested in reducing the average symbol energy. And that takes some time to sort of, there is huge variance, which is as expected with the reinforced algorithm. But it takes some time to sort of converge to a given value, and we can see that it's very close to the energy of 1, which we want it to be. So this is like learning essentially something which is very close to the true QPSK. So here I have the constellations which we learn at sort of different iterations. You can see that I'm sorry, this is not too legible, but the smaller dots here, I don't know if I can annotate here. So the smaller dots here are the true, you can say, locations. So initially we start off with some random places. And then as the training progresses, we see that we sort of get a structure. These are the ones which are learned by the agent. We get a structure which closely represents the true constellation, but with a certain rotation and a translation. So turns out this is fine, because when we do minimum distance decoding, essentially what it will try to do is sort of construct a decision region which looks like this. So this is all right, and obviously the performance is good as evidenced by the bit error rates which we achieve. So now this was just the transmitter. Can we do a similar thing for the receiver? Like how hard, or what would the difference be in this case? So what I did here is I fixed the transmitter initially to use a predefined modulation. So I used QPSK again. And then the receiver is parameterized by a simple neural network, a two-layer neural network I think I used for this. And then here I had to experiment with the different sort of, you can say, exploration strategies, because the receiver can be thought of essentially as a bandit. So it's basically choosing what bit string to give as an output so that it receives the maximum reward. So it's like a contextual bandit in a way. So initially I used like basically epsilon greedy, and that didn't turn out well at all. I used to always sort of exploit very quickly, even though I changed my epsilon. So I had to switch to using like the Boltzmann with the softmax exploration with a pretty high temperature, so that it would like sort of all the actions would be explored enough and kept sort of relevant until the future iteration. So and again I used just vanilla policy gradient to train this receiver for 500 iterations with around like 500 steps for each iteration. So this is what the receiver learns essentially. So at around 200 iterations itself, it's sort of starting to learn the ideal decision regions which we want, which we expect a QPSK demodulator to have. But there are certain regions which are sort of, you can say, where it can introduce bit errors. By 900, there is not much significant change in the regions, but it's a lot smoother, and this is like the best performance I could get off with the Boltzmann exploration. With epsilon greedy, these things were like very bad. They were like highly nonlinear regions, and it resulted in a very high bit error rate. So this is the final bit error rate I was able to obtain for a single agent receiver. It's not doing as well as I expected it to do, but then again, this is just a proof of concept, and maybe I should have trained it for a bit more iterations with a few changes with the exploration and so on. So in conclusion, I guess it's definitely possible to learn these simple radio modules which are part of a bigger radio design through reinforcement learning. I'm already exploring learning these things jointly, so that, and they sort of tend to learn, I'm seeing that they tend to learn the QPSK result modulation schemes. But again, the results I got weren't too great, so I'm still working on them. Yeah, and that's my presentation.
Yeah, excellent. Yeah, thank you very much. So I guess the first question is a clarification question. So is this are these experiments like from yourself, or are these reproducing experiments from this paper that you were reading?
So the paper I read actually tries to do directly learn. Let's say you have a transmitter and a receiver in some channel. What do they learn? So they are exploring that. But that is a much harder problem to solve.
Okay.
You have to throw more resources at it and hope that it learns well. What I tried to do was just give a proof of concept and see if this makes sense.
Okay.
Also, the authors, they just explored vanilla policy gradient. I tried actor critic. I also wanted to do natural policy gradient because it sort of tries to do well, and I think the convergence is improving. But I ran into some stability issues with the Fisher information, inverse of the Fisher information matrix. So that is one more sort of avenue which I'm exploring to learn better.
Yeah, there are regularized version of the natural policy gradient that avoids the stability issue that you can look into.
Yeah, and also,
yeah.
Sorry, go on.
Yeah, so a more concrete question is related to, so in your first setup, you are learning the transmitter's policy. So this is about how, like, where you are placing your each symbol and map that to a complex plane, right? So assume you have 4 symbols, and how is this gonna place it? So this seems to be a pretty non-trivial problem. It's definitely the non-convex optimization problem, even if you receive the full information feedback as a reward. And you are saying that your receiver receives this and then somehow compute the reward and send it back to the transmitter. So how would you like transmitted? Does it go through the same noisy channel? So the feedback is received by the transmitter,
I had to mention that, but yeah. So what we have to keep in mind is all our current radio systems like LTE and so on, they already have this backhaul channel, which sort of transmits something called as a channel state information. So it's very popular in Wi-Fi and so on. So it basically tells the transmitter, you know what, the channel is so bad, you have to change some of your transmission parameters to help me, decode better. Otherwise, I'm not going to get anything. So, but what in the current state is the transmitter falls back to something which is predefined. So there is no adaptation, or rather the adaptation is quantized. It says, okay, either I do full throttle, some great modulation scheme, and if it doesn't go through, I will switch to a very bad scheme where I'm sending only, like very vital information. So all that you can say that the concept of the environment and the agents receiving feedback based on how the other agent was able to decode or not is already present in the current infrastructure, which makes this problem more, relevant to the setting we already have.
Right. Cool. Yeah. One last question. So your I guess you talk about this white noise, additive white noise channel, like which is quite standard and a well-studied theoretical model, and well the optimal like packing of the space will give you, say, the optimal coding rule that's robust against any distribution of the input. But what machine learning and reinforcement learning is able to do seems to be like breaking, like it seems to be working in an environment where your theoretical assumption is no longer true, and also to handle like the different realistically observed distributions and adjust the corresponding coding policies accordingly, right? So from your talk, it looks like you are treating this optimal thing as a baseline, and that's the best that you can get, and see if your algorithm can learn that. But I think one good suggestion is that you can try some like settings where it breaks the theoretical assumption and it has some non-trivial and skewed kind of distribution of many different symbols, and to see if your agent is able to learn to use a higher energy or to assign a higher space to put that particular symbol in the complex plane, so that you can do a more data adaptive kind of a coding policy that significantly improve over the baseline.
Yes, that is definitely, I did experiment with that. So for example, when I'm training either of the agents, what I can do is I can already set what is the sort of the signal to noise ratio in my channel. So what is basically my variance of the Gaussian noise I'm adding. So I sort of try to vary this, and it's natural that when the noise is really high, my agents would try to sort of put more energy. So the average symbol for energy used to shoot up. So what I did was I sort of averaged across these SNR, runs. One definite thing I could do is sort of introduce a true environment where everything is stochastic, in like not only in terms of what noise it adds, but then how it adds the noise and what sort of delays it provides and so on. So I definitely need a more realistic environment and simulate it. But then again, simulating all the imperfections wireless signal goes through is also very tricky. So
yeah, understand. Yeah, thank you. All right, let's move to the next talk. So upcoming next, I think is another theoretical talk. So could you set up?
Yeah. I hope you can see my screen. Okay. So I'll be talking about the NeurIPS 2019 paper called Dual Dice, and it's about estimating the marginalized the marginalized importance weights that we saw in the OPE lecture. And yeah, let's begin. So before are you able to hear me?
Yes, we can hear you well.
Okay. Yeah, so before diving into the paper's details, I just want to do a quick recap on what we learned. So we saw that how to do off policy evaluation in RL, specifically in the finite horizon MTP setting, and we talked about the estimators like importance sampling W robust, which suffered from curves of horizon, But then we leverage this formula that the value of policy pi can be written as the expectation over reward, where the state in action is sampled from the distribution d pi, and then that inspired us to use the estimator called marginalized importance sampling estimator, which is basically an adaptation of this equation in the finite horizon setting. And here we approximate this d pi separately. We estimate d pi nu from the data itself, and the d pi hat from the recursive estimation procedure. And dual dice is again now approximating about these importance weights. So before studying the algorithm, let's talk about the problem setting here in dual dice. So in the dual dice, instead of finite horizon MTP, we now have an infinite horizon discounted MTP, where there's a state action reward, the transition kernel, and we have the gamma, which is the discounting factor, and the beta, which is the initial state distribution. We also have collected data, which is in the form of quadruples, state, action, reward, and the next state. And we have it for n time steps. The one thing to note here is that this kind of data is in dual dice. There's no assumption on the type of policy that collects this data. So in the most general setting, this data can come from multiple non-Markovian behavior policies. So it doesn't have to come from one single Markovian behavior policy. And then this paper tries to estimate the marginalized state action importance ratios that directly, instead of approximating the numerator and denominator separately. And once we find the marginalized state action importance ratio, we can calculate the value of a policy by using this simple formula. So the key idea in dual dice is that they have a objective which looks like this. There's an expectation over the distribution or the data, and inside there's a Bellman residual. Here nu is any function from any bounded function from state action to real number, and b pi is the Bellman operator in when the reward is 0. So it's if you like have a 0 reward and you apply the Bellman operator, then this is the kind of expansion you will get. And a nu minus b pi nu can be thought of as the Bellman residual. And here there's another term here which where the expectation is over the initial state distribution and the action taken. So they showed that if we optimize this function, then the Bellman residual of optimal Bellman residual is equal to the importance marginalized important weights itself, and this can directly be used to calculate estimate the these weights. However, the problem here is that there's a square term here and there's a expectation inside. So and the expectation is over the transition kernel. So when we calculate the gradients, we don't have the actual transition kernel available, and we will have to estimate them. And in the case of continuous action space or continuous state space, it can get tricky. So they try to change this objective into something that's more easily optimizable. So for that, they use the idea of Fenchel conjugate. A Fenchel conjugate of a convex function is a function which looks like this. So here, if you have a convex function, its Fenchel conjugate will be written by this formula. Here the function that we're considering is this x square function here. So if you think of the x square function, the Fenchel conjugate of x square function is x square itself. As you can see that this is a simple maximization problem, and you can calculate that the optimal zeta is equal to half x square. So using this kind of transformation, they transform this square into max over zeta, and x times zeta minus half zeta square, and so we get rid of the square term here. And if you see here, if you see this in our maximization problem, then the optimal value of zeta is actually equal to this Bellman residual. And when you substitute in the value of optimal nu for which minimizes j nu, then we get the marginalized importance weights from directly from the zeta star. Now we here now we have a max over the Bellman residual, but we still have to sample from the transition kernel. So they use an interchangeability principle to overcome this limitation. So interchangeability principle is a simple principle where you have an expectation over a max of some function, and you convert it into a max of expectation. So here the max is over the random variable xi, and so the expectation is over random variable xi, and the max is over a scalar mu u, and in the second term on the RHS, we instead of max over nu, we have a max over function b, which is we have max over function space actually, and the b takes as input the random variable xi, and it outputs a scalar. So this kind of interchangeability principle is useful, as we now are able to remove the max from inside the expectation to outside, and we get a min-max optimization problem. And we can also see that the zeta here that we had before is now not a scalar but a function from state action to real numbers. The Dual-Dice paper shows that the MSE for their estimator is actually I think I missed to mention this, but they parameterize the nu and zeta functions by say a neural network or a linear function approximator, and then the mean square error depends on the approximation error, like based on the if the the new if the function classes are general enough, then approximation error will be low, but the optimization error is hard to characterize, like in case of neural networks. And the third term here is the statistical error, which says that as n tends to infinity, the error for statistical error decreases significantly. We can also contrast it with the marginalized importance sampling estimator that we covered in the class. So we can see that we have a different setting here, which is discounted infinite horizon MTP. This dual-dice estimator directly estimates the marginalized importance ratios instead of estimating the numerator and denominator separately, which allows this estimator to also work for continuous state and action spaces. Whereas the marginalized importance sampling estimator only work for continuous action spaces and not not continuous state spaces. It also uses function approximation, whereas MIS didn't. And the data in Dual-Dice can come from multiple non-Markovian behavior policy, whereas for MIS it came from a single policy mu. In the case of now we can talk about the evaluation. Here they consider two environments: the card-pull environment and the reacher environment. The card-pull environment is a simpler environment than reacher, and here we can see that the blue line is Dual-Dice, the red line is the true value, the green and the orange lines are TD methods, where they try to construct a if you remember, there's like a Bellman equation for d pi as well, and from that you can obtain a TD error. You can write it in terms of a TD error equal to 0, and they try to optimize that. Yeah. So these kind of methods uh, have been studied in the past, and they compare with those methods. And then they also compare with the importance sampling method, which we saw in the class as SSD-IS method. That's the importance sampling method that they compare against. And we see that the dual dice estimator works well in the cardpool environment, and the importance sampling estimator works really well as well when the alpha. So alpha here is the is how much the target policy deviates from the original policy. So as alpha increases, the estimator tend to get better. But for low alpha, dual dice still works. And for the research environment, which is a more complicated environment, there's a the bias for the other estimators is pretty high. So that's all for my talk. Thank you.
Yeah, thank you very much. Question from the audience. I'll start with one question while you guys make up your mind what to ask Rohan about. So you talk about the connection to IMIS that we covered in the class by saying that this one handles function approximation, and it's directly approximating the marginalized importance weights rather than the numerator and denominator separately. Could you also compare with the fitted Q iterations that we covered in the last lecture when we talk about function approximation, right? So what are the key differences that the dual dice is making and approximating that the FQI or FQE isn't approximating?
I don't exactly remember the fitted quiz approximation that well, but I remember it was related to the fictitious estimator.
Yeah, the technical analysis is related to that, but the algorithm wise, right? So this is very similar to Q function with function, Q learning with function approximation, except that it is operates in offline setting.
Oh, okay. Yeah, so sorry, I don't remember it that well right now.
So a reminder is that the Q learning with function approximation uses a linear approximation to the Q function, or the neural network approximation to the Q function if you are doing the DQN, right? So what is the key difference of this comparing to the function approximation approach that simulates the Bellman optimality equation or Bellman consistency equation with just a Q function approximation? Yeah, does dual dice like also approximate the Q function, or it only approximates the importance weights?
It only approximates the importance weights. It does not approximate the Q function. The neural network is used to approximate these is used to approximate these nu and zeta functions, which are implicit in the optimization equation, but they're not equal to Q function or anything else.
Yeah, but what does the new function represent?
I think they don't represent anything. The zeta function is equal to the importance weight.
Right. How about the new function?
I think the Bellman residual for new function is equal to the zeta function, and it's equal to importance weights. But I don't think
could you reshare the screen and go to the equation so we can talk about it?
Yeah, sorry. Yeah, so the Bellman residual for the new function is equal to the importance weights, but I'm not sure if
What does B pi mean here?
B pi is the expectation over the next state and the next action. And there's like a gamma here. It's like the gamma p pi matrix product that we do when we write a Bellman.
So what is a function nu that satisfies this equation, these constraints? Yeah, so you are starting from state SA and you are taking action according to pi, right? You are taking your transition into state S prime. Then in the future you are taking action according to A prime.
Yes.
According to pi, right? So what is a function nu that satisfies this equation? Now what is this equation?
So I think nu is any general function, but I'm not able.
Yeah, nu is any general function, but only like a subset of this general function actually satisfies this equation.
Oh,
right?
I see.
And what is this equation? Can anyone else help out if Johan, you're not confident with your answer? Yeah, T is a state transition, by the way. T is the dynamics.
It looks similar to the Bellman equation for D, like the state action visitation measure, but yeah, I'm not sure exactly what nu is.
Right. So the only difference from the Bellman consistency is a missing it's a missing R, right? So that might be something that might be something that's missing, but this is very similar to the Bellman consistency equation. So suppose you add R of SA, right? Suppose you add R of SA in front of this gamma times this E thing, then you recover exactly the Bellman consistency equation. And then the objective function you are minimizing is to find this new function such that I think this might even be coming from a typo. Because if you look at it, it doesn't even use the third element in the quadruple data that you receive, right? So I think there's a missing RSA in front of this this gamma expectation thing.
It actually uses the last S dash from the quadruple in the transformed function, which looks like this. So here it uses S dash from data.
But I mean the force. I mean the force element. So unless you don't observe reward, right? So you also observe a reward, and reward is never really used, right? So the where the reward is used is either like should be in the equation over there, right? So and then this becomes a standard Bellman consistency equation with respect to policy pi, right? And so what this is really learning, and what this new function is approximating is this Q pi function, right? So this unknown Q pi function, and you are using a function class to try to approximate it, and you are minimizing the mean square error of that. So there's this duality, like representation between the importance weights and the new star function, which it's coming from the dual linear programming representation that we learned in the class, and there's a connection between this new function and the importance weights function according to this relationship. And this is really their main contribution, is to establish that, and then the remainder of the paper is bells and whistles that tries to leverage this idea and then solve the practical optimization problem, and then demonstrate that this idea actually works.
Oh, okay. But there's no typo here, that like reward is never present in this part.
Yeah. So I'm not sure. They must be using the reward somewhere. Otherwise, like it doesn't make sense. Like what is it that are you optimizing? Yeah, what is it are you trying to approximating?
Yeah, they use the reward in the transformed objective, but in this objective we don't need the reward to see that new star minus b pi new star will give the importance weights.
Oh, I see. So
Yeah.
they're optimizing some new function, and this new function is like I think it could be some like transformed version of the QPy functions, right? So whenever you learn the new function, then you can use this to construct the QPy function, which can be used to get the final policy evaluation.
Okay, I see. Okay.
All right. Yeah. Yeah. Excellent presentation. So now let's move to the next talk.
Hi, can you hear me and see my screen?
Yes, I can hear you.
Okay, so hi, my name is Eileen Tuan and my coworker is Wanlong Zhu, and our project topic is about an overview of reinforcement learning in test generation. So our work, we would like to try to progress of reinforcement learning on test generation and review the literatures and unify their formulations. And then we conduct a small experiment to have a fair comparison between these variations. So test generation is a task that aims to generate a sequence of words that is fluent and matches with a specific goal. And this goal could be that we would like to generate a proper machine translations or have a engaging conversational agents, or just want to generate a story that is written as Shakespeare. So in this task, we define the generated task as Y, and it is composed of a sequence of a sequence of words that are represented by Y1, Y2 to YT, where Y1 is a generated word at the first time step and so on. So for a generative model for test generation, we can formulate it as trying to find the probability of Y that is equals to a product of probability that is P, probability of Y1 times probability of Y2 given Y1 and so on. So a typical way to formulate test generation as Markov decision process is that we take the generated text Y as an episode, and each time steps, the generated words YT is defined as the action conducted at time step T. And for each probability of word T, YT, it is defined as a policy given a state and predicate action. So the probability of Y, the generative model of test generation can then be presented as a policy of action 1 given state 1 that times policy of A2 given state 2 and so on. So the next thing to formulate it as MDP is that we have to define a reward function for this task. And a typical reward function is using the evaluation matrix in test generation. And widely used one is the what overlaps between the generated text and a given reference. So for example, the generated translation and a given a reference of the ground truth translation. So, so in this setting, if we get a reward, we then can compute typical ways to compute the state action value of this reward using a discounting factor gamma. But in this case, only when we end the episodes that we can get a rewards. The reward is fast. Then after getting this action value, then people often update it using reinforce or policy gradient, and just take the gradient of the policy, the log of the policy, and then multiply it with the Q value. Or sometimes people will, most cases, people will actually multiply with the advantage function, that is Q value minus the value function. And there's also other variations, but because in our project that we are trying to unify the different Q values among different literature, so we skip the notation of the baseline here. However, because the evaluation metrics, the normal evaluation metrics for test generation are still in debate, that many people will think that current evaluation metrics is controversial, that it cannot really evaluate if the test is high quality or not. So another way is to use generative serial network to predict the reward. Hi, Wenrong, can you?
Hi. Yeah, speaking of this, we can first take a very quick glance at what GAN does. GAN is an application of reinforcement learning, and it has two parts. Could you please move to the next page? The first part is a generator that is trained on the real world data, and it aims to generate plausible data, which will later be served as a part of the input to train the discriminator. The second part of GAN is the discriminator. The discriminator takes both the real world data and the fake data generated earlier by the generator, and it is trained to distinguish between these two. Both the generator and the discriminator are neural networks. The generator output is connected directly to the discriminator input. So through backpropagation, the discriminator's classification provides a signal that the generator used to update its weights. We can apply GAN to text generation, in which the reward is considered as the estimated probability of being real by the discriminator as the reward. Could you please move to the next page? In this slide, next page, please. In this slide, we give an overlook of the whole process of applying GAN to text generation. In the figure on the left, G stands for the generator and D represent the discriminator. As a start, the generator is trained with the real world data to produce predicted text sequence. This problem can be interpreted based on reinforcement learning. So at time step T, the state S is the current produced token, Y1, Y2 to YT minus 1. And the action is the next token YT to be selected. As for the other part of the sequence scan model, the discriminator is trained by providing positive examples from the real sequence data and the negative examples from the synthetic sequence that is generated from the discriminator. It provides a guidance of improving the generator. So the dy is a probability indicating how likely a sequence y is from the real sequence or not, which is treated as a reward. So the more likely for the generator to fool the discriminator, the higher the reward will be. In the paper that introduced GAN, the generator tries to minimize the following loss function, while the discriminator tries to maximize it. In this function, the first part of the equation is the discriminator's estimate of the probability that the real data instance is real. And the second part of the equation is the discriminator's estimate of the probability that a plausible loss generated by the generator is fake. So the generator can't directly affect the first part. So for the generator, minimizing the loss is equivalent to minimizing the second part, which is trying to fool the discriminator. The benefit of using the discriminator as a reward function is that it can be dynamically updated to further improve the generator iteratively. Once we have a set of more realistic generated sequence, we should retrain the discriminator model to maximize this target function. Next page, please. However, the discriminator can only provide a reward function for a finished sequence. If we only obtain a reward after this whole sequence is generated, then the reward is going to be very sparse. It will be much better if we can obtain a reward for each step during the generation. To evaluate the action value for an intermediate state, we apply Monte Carlo search with a rollout policy to sample the unknown tokens until the end of the sequence. We represent an n-time Monte Carlo search as this equation. To to reduce the variance and get more accurate assessment of the action value. Next page. We run the rollout policy starting from the current state till the end of the sequence for n times to get a batch of output samples. Then we have this updated reward function. And we can see that when the time step t is not finished, then it will be the average of the predicted samples. And if it was finished, then it will be the predicted value given by the discriminator. Okay, that's perfect.
However, because in text generation, the action space is typically quite large. And so using multicolor search, it could be really time consuming and exponentially grows in training text generation. So some people try to propose other methods to get the state action values for each time steps. And one way is called the reward every generation steps. So in this work, they randomly pick a subsequence as the input to the discriminator, and then train the discriminator just using the subsequence of the generated sentence of the generator. And then they can actually get a discriminator score for each subsequence when training the generator. So they directly use these scores as a state action value as for every time steps. So, before the next move, we would like to first generalize the test generation into conditional test generalization, because this is more common cases for real applications such as neural machine translation, dialogue generation, and summarization, and etc. So in conditional test generation, the main difference is that we actually have an input X as the condition. So now the state 1 will be the X, and state 2 will be the concatenation of action 1 and X. So then we try to unify the prior formulations of the above methods using in conditional test generation. So we can find that in the original sequence scan without multicolor search, that they are actually computing an estimated state action value using the discriminator score. And multicolor search also use the same thing. And RGS is actually trying to compute a discriminator score sample from one of the stack action value. And on the generator's side, the original sequence can directly just use the final steps of a discriminator score, and then use a gamma. Normally, gamma factor is the discounting factor is set to 1. So the update of G is like this. And when using multicolor search, that we use a Q star value here that is represented as the average of the multicolor search results. And then for RGS, because the discriminator is actually trained to randomly sample from one of the estimated station value, so they heuristically assume that this estimated station value is for these time steps. So in our experiment, because we found that the results on text is really hard to evaluate, so we cannot get a really guarantee results of these texts and cannot find the analysis of them. So we use toy experiments on this. We use a task called counting sequence. So in this task, the action space is digits that from 0 to 9. So there are 10 possible discrete actions. And then we given an input sequence X from X1 to Xn, where N is arbitrary numbers. And then the correct output Y that is composed of Y1, Y2, Y3 should adheres to the following rules. That K is sampled from 1 to an arbitrary number, and Y1 is K minus 1, Y2 is SK, Y3 is N minus K. And this means that we randomly select a number in the input sequence and then count how many tokens is on the left of this selected token and how many words on the right of this selected word. So for example, an input sequence 78265, the output can be 074 if we select 7 as the SK and count that there is 0 words on the left of it and 4 words on the right of it, and so on. So we could have 5 possible outputs. So this test is designed to be many-to-many because in many text generation texts, actually the output space is there are many kind of acceptable outputs. So this is more real. So in the experiment, we evaluate both the precision and recall. So in precision, we can consider it as that if we randomly sample some output from the policy of this method, of the model trained by this method, what is the accuracy of this output? And recall here means that if we randomly sample some outputs from these from the models trained on these methods, what is the percentage of the output that could be covered? So in the experiment, we mainly found that so an MLE method is just a supervised learning method without using anything like reinforcement learning. So in the experiment, we can find that actually reinforce quickly get a high precision, but it get a really bad recall. It will just find the correct answer and then keep moving on it and cannot find the real distribution of the data. But for other methods such as scan, and even though that it find a better, it could find it use a better reward function to substitute the reinforce, but the precision is just slightly better and the recall remains the same level, but it didn't really outperform the supervised learning. And so in our work, we mainly refer to these papers, and we would like to also note that there are actually some variations on using adequacy algorithm or using offline policy gradient to optimize this. But we didn't include it here. And we finally want to say something about our reflection. So during this project, we found that the training of reinforcement learning on text generation is really unstable and difficult to tune. And and also, even though GAN can relieve the problem of unconvincing reward function, the training will actually becomes even more unstable. So the above might be the reasons that actually we found recently there are less study work on this area. They are less likely to try to improve text generation using these kinds of methods. But however, there are still many methods. There are still many tests that are trying to use RL in something like text generation, but they are not improving the algorithm part. They are trying to apply it on a new task. But what we want to know that is that we found that most of them is directly applying reinforce to their methods. However, in our experiment, we can find that reinforce actually could have a really harsh modulus problem in training. So that might not be a really good idea for current research to keep using reinforce. And so these are projects. Thank you.
Yeah, thank you, Yu-Xiang and Wen-Rong. And this is an excellent application of reinforcement learning. And I have some questions regarding the problem setting. So is this episodic or infinite horizon reinforcement learning? Are there discounting factors? And also like typically in a reinforcement learning problem, when we have an MDP model, the reward function is assumed to be fixed, right? So we can, sometimes you can only sample from it. In other cases, we can actually observe the reward given state and action. And is in your problem, is a state transition deterministic or stochastic? Like, do you know the state transition, or like what is the key challenge of running reinforcement learning in this problem? How large is the state space and how large is the action space?
Okay, so the state space, I think it is really exponentially growing. I don't know how much it is. And for the action space, it is normally, I think, more than 10,000. And so since the action space is more than 10,000, so the station space is actually exponential of 10,000 power to something.
Mm-hmm.
So
10,000 to the power of t, right? And t is the length of the sentence you want to generate. Yes,
that's right. And so for the in normal setting, the discounting factor is normally set to 1. So seldom researcher change the discounting factor. And I think, can you remind me of your other questions?
Yeah. Is it episodic or is it the infinite horizon?
I think it is episodic. So they will just take the each sentence generation as an episode.
Okay, and in the conditional case, your initial state is probably given by this context X. And in other cases, it is the first token that your sequence receives.
Yes.
Right.
Yes.
And the other question is that typically, like in reinforcement learning, you're learning the optimal policy with respect to a fixed reward function. And in your case, it looks like the reward function is determined by a GAN. And are you updating GAN, or are you having this inner loop, outer loop thing that you keep GAN the same for a while for the reinforcement learner to get to the optimal policy before updating the reward?
Yes. So in our experiment, we do two things. In reinforce, the reward function is fixed. It is using an evaluation matrix called BLUE. And in our GAN setting, we did not fix the GAN. So the reinforcement learning is trained while the discriminator is jointly trained. It's relatively training, yeah. So
okay, they're jointly trained. So the reward function and the policy are updated at the same time.
I think they are in iterative train.
Oh, okay.
But we did not train until we did not use policy gradient or reinforcement until the converge and then update the discriminator. We just set a fixed steps. Yes.
Okay. Okay. So I think a more relevant literature from reinforcement learning to this problem is probably the two-player game. So there are two-player games settings where there are two reinforcement learning agents playing against each other and trying to beat each other. And in this case, I think that's a better model for potentially your problem. And another thing that since the key challenge is a astronomical sized state space and action space, and the typical trick that people use in the RL literature to tackle this is to use function approximation, right? So instead of just using the tabular state where you enumerate all y1 to yt as I guess tensor product of its one hot representation, so you get an astronomically large state space. So yeah, maybe you have already used that. You could use some kind of a feature embedding of that, and then use a mean embedding, maybe weighted towards the end of the sentence or so on, so that you have a finite dimensional feature representation of the entire history of your sentence. And then that will make the learner learn significantly more quickly, and it will also maybe address some of the stability issues in these applications.
Yeah, I think that's a good idea. And I think in real experiments, actually the state is already represented by features, but seldom researcher think it in this way. So I think it's quite interesting. Yeah.
Okay. Yeah. Sounds good. Yeah, and excellent talk. I think given that the state people are still using reinforce, maybe exploring some of the stronger algorithms with function approximation, like could yield interesting new findings in natural language processing context.
Yeah. Thank you.
All right.
Thank you.
Good. Yeah. Upcoming next is Kai-Chi, who's going to tell us about the optimal off-policy evaluation for multi-arm bandits.
Hi, can you see my screen?
Yes.
Great, thank you. Hello, I'm going to talk about minimax of policy evaluation for multi-armed bandits by a Berkeley group. This paper is targeting on a multi-armed bandit problem. In this case, we have action states, and in this paper, it is assumed to be finite, and the actions we can ever take are indexed by 1, 2 through k. And furthermore, we have a collection of reward distribution. For each action, we have a distribution of the rewards. And our target is to evaluate the value function of arbitrary policy, which can be potentially randomized. Here, the value function is defined differently from the MDP setting. Here, the value function is the expected reward under a specific target policy. And in this paper, we are targeting on an off-policy evaluation problem, in which case the behavior policy we used to collect a set of action reward pairs can be different from the target policy. The only information we have is the set of action reward pairs and potentially the behavior policy, and our target is to evaluate the value function of arbitrary target policy. We will start from a simpler case where the behavior policy pi b is known as a prior. In this case, two estimators are most popular, which have already been covered in the class. One is the plug-in estimator. The idea is to evaluate the reward of the average reward of each action using the reward action pairs ever collected, as long as at least one of this action has been taken at least once. And if this action has never been taken in the behavior policy, then we have no choice but to plug a 0 here. And at the end of the day, we will estimate the value function of the target policy by a weighted average of our estimation of the reward. It is known that this plug-in estimator has lower variance, but it is biased. The reason it is biased is that if one action has never been taken, then what we can do is to plug a 0 here, which obviously is biased. Another kind of estimator is the importance sampling estimator. It is similar to a Monte Carlo estimator, but we add a scale for each reward, where rho A is the ratio between the target policy and the behavior policy. It is known that this importance sampling estimator is unbiased, but it usually has a larger variance because the variance from each sample is scaled up by a factor of rho A, which can be arbitrarily large. And in class, we talk about a third kind of estimator, switch estimator, which combines the benefit of plug-in estimator and importance sampling estimator. The key idea is that if the ratio between target policy and behavior policy for specific action is smaller than a threshold, then we will use an importance sampling estimator. Otherwise, we will use plug-in estimator. So initial question to us is, what's the performance of this switch estimator? And in this paper, upper bound on the mean square error of this switch estimator is given. The proof, as in proposition 1, the proof of this property is based on standards bias variance decomposition. I will write it on a Jamboard. Here, the mean square error of one estimator can be decomposed into a bias term and a variance term. We know that the important sampling estimator is unbiased, so only the plugin estimator will contribute to the bias term. So the bias term will be bounded by and furthermore, the variance term, to bound the variance term, we will make use of the fact that so we can bound the second term and the first term can be bounded in the same way as in the bias term, while the second term, one can use easy calculation to bound it by to achieve the second term in the right hand of the equation. One can notice that in the proof, we used little information about the plugin estimator. So actually, the author claimed that the plugin estimator doesn't play an important role in the switch estimator. If we replace this plugin estimator with an estimator that returns 0 to every action, then we will get the same performance bound. The reason is that if rho is large enough, then the variance caused by an important sampling estimator will be so large that it's better to use any other estimator, which a lower variance, even if it is biased. The next question to ask is how to select S, how to determine which action we should use plugin estimator and which action we should use an important sampling estimator. In class, we mentioned that if the ratio between behavior policy and if a ratio between target policy and behavior policy is larger than a threshold, we should use plugin estimator, and otherwise we should use important sampling estimator. And in this paper, a more formal equation is given. We will need to solve a convex optimization problem, as it's given above. And it is argued that if we will choose S to be those actions whose corresponding solution VA is non-zero. And the author proves that if we use this option of switch, then we will get a performance bound which is optimal as for any option of S up to a factor of constant C. Another question to ask is if the switch estimator is optimal. To answer this question, we will need to find the minimax rate of this estimation problem. In other words, it is the lowest mean square error an estimator can ever get. To get a minimax rate, this paper made up a multi-armed bandit problem. The problem it created is that we have two actions, A1 and A2. If you choose action A1, then with probability 1/2, you get a reward R max. And with probability 1/2, you get reward 0. And if you choose action A2, you will get reward R max with probability 1/2 plus delta A. And with probability 1/2 minus delta A, you will get 0. And if we optimize over delta A, we can get a performance bound of this of any estimator can ever achieve. As is given in theorem 1. And if you compare the theorem 1 with proposition 1, you will notice that the mean square error of switch estimator is optimum up to a factor of constant, which indicates the mean square error of switch estimator differs by the minimax rate up to a factor of constant. This indicates that switch estimator is optimum up to a factor of constant. Then another problem is that what if the behavior policy is unknown? In this case, one cannot use important sampling estimator or switch estimator. And the only estimator suitable in this case is plug-in estimator. And they also further claimed that the minimax rate is no longer suitable. The reason is that for any target policy, one can always construct a bad behavior policy so that for any estimator, we have a lower bound of C times R max squared. One option of this behavior policy is to always take only one action with probability 1 and never take any other actions. We can make this action to be the action that is taken with lowest probability in target policy. In this case, we have 0 information about the actions that has never been taken in probability, in behavior policy. So instead of using the minimax rate to estimate whether an estimator is optimum, they also defined competitive ratio, which is the ratio between the mean square error of one estimator and the minimax rate given the behavior policy and the target policy. So the next question to ask is the competitive ratio of the plug-in estimator. And in this paper, they also proved that it is upper bounded by C times the support of pi t, where the support of pi t is defined by all the different actions this target policy has ever taken. The proof of this bound is again based on the bias variance decomposition. We can bound the variance by its bias plus the variance. And we will use the same way as in proposition 1 to bound the bias. And as for the variance, we will further decompose it as using the law of total variance. where NA is the number of times this action has ever been taken in the behavior policy. And at the end of the day, we will bound each term separately to get the performance, the upper bound of the performance. Compared with, from the definition of competitive ratio, we know that compared with a plugin estimator, so compared with the switch estimator, the plugin estimator will get a higher mean square error up to a factor of c times k, where k is the total number of actions. The next question to answer is whether the plugin estimator is optimal. To do that, what we need to do is to bound to get a lower bound on the competitive ratio of any estimator. And the author proved that this bound is S divided by log of k, where S is the support of the target policy. We can notice that there is a bound on the minimax rate of competitive ratio and that of the plugin estimator. This indicates that there is a gap between the plugin estimator and the optimum estimator. And the plugin estimator is optimum up to a factor of logistic. And furthermore, we know that by removing the information of behavior policy, the mean square error will be increased by a factor of at least S divided by log of k. I only covered a subset of results in this paper due to limit of time. And now I'm going to show some results from this paper. The first result is the mean square error of plugin estimator, switch estimator, and importance sampling estimator. We can see that when the sample size is small, then the plugin estimator will have a smaller mean squared error, and importance sampling has a larger one. And as the sample size increase, the error of importance sampling estimator decrease at a relatively fast rate, while plugin estimator almost not decrease. So at some points, plugin estimator will have a larger error than importance sampling estimator. And finally, switch estimator has lower error than any other, than either of the two estimators. And as for the competitive ratio of plugin estimator, we can see that as we increase the support size of the target policy, the competitive ratio increases at a linear scale, which fits our prediction. Thanks for your attention about this paper, and now I'm willing to accept any questions.
Yeah, thank you, Kai-Qi, for the presentation of this very technical paper about a simple problem on the multi-arm bandit setting. So the first question I have is regarding this figure that you shared just now. So it seems a bit counterintuitive from the what we covered in the class, like the figure before, the previous one. Yes, this one. So in the class, we talk about how the plugin estimator, so as the number of data points goes to infinity, it actually is asymptotically efficient, which says that no other estimator can be better than that when n is extremely large. And on the other hand, the importance sampling estimator can be beneficial when the action space is large and when the plugin estimator is suffering from a large bias due to many of the action hasn't been visited by many times yet. So why is it different? So what's the difference in the setting that contributed to this seemingly contradictory like experimental results?
I think the difference is caused by the setting of this. It's caused by the setting of the multi-unbounded problem itself. The behavior policy and the target policy sorry, I don't quite remember the setting of this experiment, but the setting itself is influenced by the size of the sample, which may be different from that in the lecture.
I see. Maybe maybe when they are very similar to each other, then there are some benefits of using important sampling over plugging. Yeah, but both of them should go to 0 at a rate of 1/n if it's mean square error. Yeah, so something to look at. And another thing is that you went over some of the material a little bit too quickly. For instance, how one can choose this S star, right? So is the final decision rule still a thresholding rule on the pi over mu, or would you get something? What is the space that you're optimizing over?
We are optimizing over a convex problem, and suppose that we get an optimal solution V star, then if V star is non-zero, then we will use a plug-in estimator. Otherwise, we will use an important.
Yeah, so this looks like something like a square root lasso kind of problem, right? So you are minimizing some one loss, one penalty, and then some approximation loss function. So what is the intuition behind this?
I think if we take the subgradient of this problem, then it will reduce to a thresholding, but the threshold will should need to be determined by actually solving this one.
I see. Yeah. So this is very interesting. So the final rule is indeed determined by the thresholding, but where the threshold is should depend on the data itself. But it looks like it depends on pi b, right? Not just the data. Oh, okay. I see. When pi b is known, right, you can actually solve this. Yeah, very interesting. All right. Thank you, Kai-Chi. So the next talk by Diraj, Ming, and Xuandong, it's going to be on a unifying view of optimism on episodic reinforcement learning.
Hi, everyone. This is Xuandong Zhao, and my group, Ming Ying, me, and Diraj will present our project for understanding this paper, a unifying view of optimism in episodic reinforcement learning. It is published on NeurIPS 2020, and the authors are Georgie New and Kyle Pikeberg. And the basic idea for this paper is that it shows that the value optimistic algorithm and model optimistic algorithms, they have the equivalent representation. So this is why they call a unifying view. Let me first introduce some settings, and then Ming will talk about the proof and show you final result. This paper is focused on episodic RL. Let's take a quick recap of the episodic RL. There are T episodes, each consists of H stages. In stage H of episode T, the learner observes the state and then choose action, receive the reward, and transit to new state. The regret is defined in this page. And in episode T, we select a policy pi from the initial state x1 T. We want to play a policy pi with high value. It is actually the estimate of the expectation of the total reward start from the x1. And optimal policy is same as what we discussed a lot of times, and the regret is defined by summation over t from 1 to k. Pay attention to k here is actually h times t. We consider the regret for all episodes and all stages. As we learned in class, we can take a linear programming approach to solve the MDP. And the linear programming in their paper is a little bit different from what we learned in class. Actually, it is like we learned prime is their due. So let me first introduce the occupancy measure. They use Q. They use a little bit different notation. They use Q here is the probability that we are in state X and takes action A. This induce a policy pi h given X and takes action A is a ratio of occupancy measure over the summation of the all occupancy measure for action A. And to find the optimal policy pi star, we can take the primal form that is maximize the values. Here value is just the occupancy measure times reward. This constraint Q here is what we learn in class is that the occupancy measure is valid, is larger than 0, and they have the value form, and this subject to this constraint is that the probability from this state to the next state, the mass of the input is equal to the mass of the output. The duality form of this linear programming is given by a simpler form, maximum the value and subject to the Bellman equation type constraint. The optimal solution to this is the V star, the optimal value function. So there are typically two ways of incorporating optimism into RL. Like we said, one is model optimistic and another is value optimistic. They both have pros and cons, and their approach is different. For model optimistic, we construct a confidence set P of transition function. This confidence set P satisfy that the divergence of the estimate transition function of P hat and the divergence of P hat and P tilde is smaller than epsilon. And for model optimistic, we jointly optimize over the confidence set P and the policy space pi to find the best policy in best plausible model. The examples are like UCRL2 or KL UCRL. For value optimistic, we directly add exploration bonus. Here we take the notation CBXA to denote the exploration bonus. And to solve that, we compute the optimal policy via dynamic programming. So we can take a look at V plus here is the dynamic result for maximum this reward plus P times V plus the exploration bonus. And the example for this type of algorithms, what we learned in class is UCB VI, and also UBEV is also in value optimistic. The pros and cons for these two type of algorithm is that the value model optimistic have the simple probabilistic analysis, just show that the transition function P is inside this confidence set P. But the model optimistic methods are complicated to implement. We need to search jointly over model and policy. Also, it has loose bounds. Best known regret guarantee are suboptimal. It is to the power of hs square root of at. But in value optimistic algorithms, it is complicated to analysis. We need recursive argument to show optimist property of V plus. But the advantage for this type of algorithm is that it is easy to implement. We just need to do dynamic programming with p hat and the R plus the exploration bonus. Also, it has tight bounds. The optimal regret bound for value optimistic is h to the square of SAT. It improved from the model optimistic by a factor of square root of s. So then Ming will show you how to show that these two type of algorithms are equivalent in some representation.
Yeah, can you hear me?
Yes.
Yes.
Yeah, okay, sure. So far, Xuandong has summarized there are usually like two type of optimistic algorithm, like model optimistic and value optimistic. And this paper tends to unify those two views from a prime dual formulation. So he already reviewed that we have a linear programming view for the reinforcement learning problem, which is covered in this course. But the issue is it requires you to know the true transition. So to practically solve this problem, they put a optimistic constraint, which is based on certain divergence measure and a set of valid transition functions. And hence they modified the primal form by putting the last constraint based on the divergence measure, and solve this like optimization problems. And equivalently, defining a similar like conjugate of a divergence based on the divergence D, which is denoted the D star, then we can equivalently derive the value optimistic dual form, which the constraint modifies the original version by replacing P with P hat and plus the quantity called a confidence bound quantity, which is defined exactly as this D star. I think this D star measure in general mirrors the definition of a functional conjugate by using D itself. Okay, so now we have the formulation of those two optimistic frameworks, and based on those frameworks, they can provide guarantees for a bunch of different algorithms based on specific choices of the divergence measure. So recall the definition of the regret bound is defined as this, where k is the number of trajectories. So the Ming theorem in this paper is if we define the quantity confidence bound based on the conjugate of the divergence measures, then the regret can be bounded with high probability by the sum of trajectory sum of time steps of the confidence bound plus a regret of order h square root t. So it is well known, since this is like non-stationary time varying setting. So this h of square root t is of a lower order compared to the optimal rate. Therefore, the mean term is really just the first large summation. So as long as we can compute d and d star separately, then we can directly bound the regret for each individual specification of d star. So the proof sketch of this mean theorem, theorem 4, is as first decompose. So their like CB d star quantity depends on a scenario value v plus, which is actually the optimal solution of the value optimistic dual form. It is the solution of this one. Then based on this v star, they can decompose. They can show the v star is a optimistic version of the true optimal value v star, and the regret bound therefore can be bounded by the gap between this v star minus v pi, and it's denoted by delta. And similar to a simulation lemma type decomposition, this delta ht can be decomposed as delta ht plus 1t plus the difference between the empirical model minus true model with a v star plus a residual term zeta. So this zeta is actually a martingale differences, since the expectation of the later term, the conditional expectation of the later term is just equal to the first term. Okay, so based on that, they can further bound this the inner product of p hat minus p of v star by relaxing it's based on the convergence measure, and it's by a simple manipulation, it's straightforwardly bounded by the d star based by its definition. Therefore, recursively apply this delta thing. They can bound this delta to be by this sum of confidence bound plus the sum of the residual terms, and plug this back to the original decomposition for the regret. They can obtain the results they stated as their mean theorem, especially like the sum of the residual term is bounded by h squared t due to the Azuma-Hoeffling inequality that applied for martingales. Okay, so based on the mean theorem, they have a lot of specifications based on the different divergence measures they chooses. So here are the examples. We only consider the tabular case, and the regret is slightly worse than the minimax rate. So to further give you a sense of why this is like a simple framework, we recover the proof for their UCRL2 algorithm to show the regret bound of s squared h cube at. So first of all, in the UCRL2 algorithm by Jack H. Peter et al., and the divergence, the original divergence is chosen as the one norm. So consequently, I think this is typo. This should be d star. So the d star can be subsequently computed based on its definition. Since the L1 norm is bounded less equal to epsilon, then it's bounded by like epsilon times h, which corresponds to this roughly this conjugate term here, and later, since they specify this epsilon to be order square root s over n, so they can they further have this divergence is essentially bounded by square root s over n times h. Therefore, the regret based on the confidence bound is computed by this way. So this summation is very similar to us. It's essentially what we learned from the class. You can re-represent this summation from T1 to K by the sum over SA and start from 1 to NTK and use the sum of square root of 1 over n is less equal to square root of capital N to get this result. And this recovers the result very easily. Yeah, but however, this bound is not optimal. But they did provide some nice framework that can leverage the benefit of model optimistic algorithms. So also make the analysis easier from the value optimistic point of view. Okay, so there are several takeaways. The first one is that we can further extend such a framework to the linear MDP setting and obtain a regret that matches like Jing et al. But from my own perspective, the one drawback is that this framework cannot incorporate the model-free approaches. For example, Q-learnings, especially because for the algorithms like UCBVI, the value iteration algorithm essentially depends on the estimate of since the value iteration uses the transition dynamic to do the iteration, it still relies on estimating the transition component somehow. So this framework cannot subsume like model-free approaches like Q-learning, so which could be their limit. And the last one would be like maybe a pessimism view for this like primordial form might be useful to derive some counterpart results for the offline reinforcement learning. Yeah, that's it. Thank you.
Yeah, thank you, Shandong and Ming, for the excellent presentation of this interesting paper. So Jergo and Sierra, I heard them talk about it in another context, and this, yeah, I think your talk is even clearer than the original authors. So one question that I have that relates what you talk about to what we learned in the class is that so we talk about the UCB algorithm for multi-arm bandit and also for the linear bandit, right? So is this linear bandit algorithm which we use the optimism for, is it considered model optimistic or value optimistic?
I think it's considered as value optimistic.
Yeah, but how we got there is to run a ridge regression to estimate the parameter theta, right? So we estimate the parameter theta, and then we are using the confidence bound for the parameter theta to somehow convert that into like a exploration kind of bonus to the different actions. Right, so
yes, that's right.
yes, I think you are calling this model to be the state transition, and it got degenerated when we deal with the bandit setting. But then if we consider the UCB VI for the Markov decision processes in the tabular case, and for the linear MDP case, right? And in that case, it is the same ridge regression estimator that we're constructing. And then we could construct an ellipsoid type of confidence intervals, right? So is that model optimistic or value optimistic?
Yeah. So from your explaining, it's more like a model optimistic.
Yeah, the boundary of these two approaches are quite blurry, as is so
yeah.
That's the reason why the results in this paper is explaining something that's quite fundamental. I think there might be like a tighter transition if you choose the right norm to measure the model optimistic parameters, you might be able to get rid of that additional factor of S in the suboptimal results that you get from the conversion. And
yeah, that's possible.
Yeah, and regarding your comment on this Q learning, right? So if you remember that the discussion from Yichen, Mengye, and from Yichen, Mengye, and Ming, they talk about this Q learning with low switching costs, and in their discussion, essentially they still need to somehow like estimate the state transitions, right? It's just the between model-free and model-based approaches, they are also very blurry because to get the optimal dependence on S, one way or another, you have to avoid collecting S-square samples for you to perfectly estimate the model itself. So
yeah, that's sorry for interrupting you. That's a very nice comment. I just really feel like the paper from Chijing is Q-learning properly efficient is really something like a model free that has no components that estimates the transition kernel. Just do the temporal difference in immediate update. But they are like they are Bernstein type somehow like to need to leverage something to do that. But the Hofding type, they give a properly efficiency with some guarantees. It's really nice because the algorithm is very simple.
Yeah, in terms of the function form, right? In terms of function form, but the analysis like still like essentially is estimating something that's So
in the proof, I agree. Yeah, in the proof, I agree. Yeah, thanks.
All right, yeah, excellent talk. So the last presentation will be from Jianyu and Yu-Xiang.
Hi, my name is Yu-Xiang. Today, Jianyu and I are going to discuss the paper, Is Reinforcement Learning More Difficult Than Bandits? This is a paper from Zhang et al. In Code 21, and it's actually very closely related to what Xuandong and Ming just discussed. So the MDP generalized contextual bandits and is often perceived more difficult due to its long planning horizon and the unknown state-dependent transitions. The major contribution of this paper is they improve the dependence on H, the horizon from square root to the log for the finite horizon MDP. In today's discussion, I will start with the setups for the finite horizon MDP, and then introduce the baseline algorithm UCSB failure iteration, which has already been discussed by me and in Yu-Xiang's class. Later, Jianyu will talk about the monotonic failure propagation algorithm that is proposed by the paper. Here in the finite horizon stationary MDPs, we will use K to denote the epochs and H denotes the length of finite horizon. We assume each reward is bounded by 1 over H. Here, the reward is slightly different from what we know in the class, which is reward is bounded by 1. The reason of rescaling here is for fair comparison with the contextual bandit problem, because we know that in contextual bandit problem, H is always 1. Though the state transition and the reward are stationary, the policy pi can be non-stationary. That is, at different H, the policy can choose different actions for the same state. Q and V are reserved for the Q function and the failure function. The Bellman equation is follows. We will use the Bellman equation to estimate to construct Q function and the V function. In the MDP problem, the agent will first pick a policy and then interacts with the environment. Then we can collect a trajectory, which looks like state, action, reward, state, action, reward. The agent can update the policy by looking into the trajectory. And then the goal of the MDP problem is to find a policy that can maximize the value function. To measure the algorithm, we will consider regrets. The definition of regret is as follows, which is a difference between two summations. The summations of V star, the optimal V function, and the summation of V pi k, which is a value function of policy pi k. The optimistic algorithm has been used in many finite horizon MDP frameworks. In this algorithm, for each k and h, we will first construct an estimation for of the optimal Q function. That is here, our construction Q hat h of SA is always an upper bound of the optimal Q function. And once we get those estimations, we can apply a gradient method to search for the optimal, to search for policy. In terms of the regret analysis, because we already know like our estimate Q hat and phi hat, they are all optimistic, then we can upper bound regret by replacing the phi star terms using our estimations. To apply this framework in practice, we need to solve two problems. The first problem is how to estimate Q star, and how to construct Q hat such that it can ensure optimism. The second question is how to upper bound the regrets using these summation terms. For the first question to construct the estimations, here we consider a model-based algorithm for the estimation. We will have these state, action, state, tuple pairs, tuples. Here we assume all the rewards are null. The first step is to estimate the transition kernel. We will count the number of SA S prime tuples and divide that by the number of SA pairs. The next step is to estimate Q and phi function. We will iteratively estimate the Q and phi function from the last horizon. And the update is according to this rule. The estimation of Q hat consists of three terms. The first and second terms are based on Bellman equation. The third term is our construct bonus function. The reason for bonus function is to ensure that your estimation is always an upper bound of the optimal Q function. Next, the phi hat is updated by taking the maximum of the Q hat. For the second question on upper bounding regrets, we can bound regrets using the summation of the total bonus. The first inequality here is by replacing phi star using phi hat, because we know phi hat is always an upper bound of the phi star. The second inequality is by expanding the summation terms, where the rewards terms will be canceled out, and the remaining term is the summation of the bonus. That is to say, the summation of the bonus term will be the dominating terms in the regret. So there is a trade-off between regrets and the bonus term. A larger bonus will ensure optimism, but it will also incur a larger regret. So the goal is to search for a tighter bonus term. Our first attempt is to apply Hofstee inequality, which is detailed in the UCSB value iteration algorithm. Here, we want to bound the difference between two inner products, the inner products of P hat and V hat, and the inner product between V and V star. This is exactly the difference between Q hat and the optimal Q function. To ensure optimism, we need to ensure those different terms to be always non-negative. Later, we can expand and write the difference as follows. Here, the second term is always a non-negative term because we know P hat the estimated probability distribution is always non-negative, and the phi hat is always greater than V star. So the goal is to bound the remaining term using a Hofstee inequality, and we will denote that upper bound by the bonus term. As you can see, this term is always bounded because V star is bounded, and this term is also zero mean because the P hat is an unbiased estimator. Therefore, we can set the bonus term to be proportional to a square root of 1 over n of SA, where n of SA is the number of appearance of SA pair. As a result, for the regrets, the sum of a bonus are the dominating term in the regrets. Then we can apply the pigeonhole principle, where we will get this kind of regret bound. The dependence on age is square root. However, the dependence on age is still not that tight. Later, Jamie will show you how can we improve the dependence on age.
Sure, thank you, Yu-Xiang. Now let me share my screen. Okay, so actually it is here. In Zhang et al.'s recent code paper, they present monotonic value propagation or MVP algorithm that gets rid of the square root h dependence of the regret bound. So their general idea are threefold. So firstly, they replace the Hofstad's inequality with Bernstein's inequality. And then they carefully enhanced the optimism requirement with another property called monotonicity. And then based on these two properties, they recursively bound the total variance in a tighter way so as to achieve logarithmic dependence on H. So let's go into the details. So firstly, replace Hofstad with Bernstein. I just displayed the Hofstad's inequality and Bernstein's inequality here, so we can see that they are quite similar. But I mean, although both of them show a 1/√n dependence, they actually have different coefficients. So for the Hofstad, the coefficients it's more static, and it's like an absolute bound. So it is like a constant, right? But in Bernstein's inequality, it is actually the standard deviation over square root n. So so we imagine that if we could bound the summation of that kind of a standard deviation with a log h factor, and then we might expect to get rid of the square root h, right? So if we use the Bernstein to substitute Hofstad in bounding the p hat and r hat, and then with high probability, we could get these two confidential bounds, right? And if we plug them into the bonus, and then we will get a Bernstein style bonus. It is shown like this. So it has three terms, and they are proportional to the previous bounds we've just shown. But there is one point that's slightly different. I displayed the Bernstein bound for the p hat here in the lower part, and we can see that there in the bound there is a v star, but in the bonus it is a v hat. This is because we cannot get direct approach to v star, so we just use v hat to substitute. But pay attention that this might cause extra difference, and this difference could be polynomial dependence on h, right? So there's one thing that we need to consider. It is how to get rid of this kind of difference. So our idea is to develop monotonicity to cover this gap, just like we use the optimism to cover the gap between the q hat and q previously. So actually previously in UCB with the most optimism, we only need to consider the difference between a p hat and p so as to achieve a no regret algorithm. And here we apply the optimism and the monotonicity to further bound the v difference between v hat and v star inside the q function, inside the q hat function. So now we claim that we eliminate 1.5 terms in the regret analysis. And there are still 0.5 means that we still need to bound the total variance of v hat, right? And that's why we adopt the third technique. So it's a total variance. It's a total variance bound by a recursion method. So first of all, with a application of Friedman's inequality along with some other small tricks, we will get this inequality. It's like the total variance could be bounded by the square root of a second moment plus some constant. And then if we recursively apply the same idea, and then the total variance would be bounded by a 2 to the power n moment, and then to the power of 1 over 2 to the n, n plus 2n factor. So we know that we assume that the summation of actually it's we know that every v or v hat are smaller than 1, so that we could easily bound the total high order moment within H, right? No matter how is the order of the moment. So that we will get H to the power of 1 over 2 to the n plus 2n bound, and then if we slightly choose n to be log h, and then everything goes to logarithmic, so that we could get rid of the polynomial H dependence. And based on all those tricks, we get the regret bound, which is square root SAK plus S square A. So S square A comes from the remaining term of the Bernstein bound. It's it's a summation of 1 over NHK of SA. And just to recap the techniques, it's the Bernstein's equality, monotonicity, and the recursive bound. So that's the general idea of MAP algorithm. But and also there are still a few open problems after this work. There are not only problems that has been presented in their discussion, but also there's one. The second problem comes from my own idea, and also there's one thing I would like to say. So in this work, we assume that the summation of the rewards in one epoch is bounded by 1, right? But actually, what I have imagined is that they compare the RL and bandit in just in one single epoch, so that if they could get rid of the square root H dependence, it is quite interesting, because even in multi-arm bandit we could only achieve a square root H dependence, right? So actually, what they did is not to consider the H dependence within an epoch. It's actually over different epochs. So that is actually what is different from my first imagination. Yeah, and I think that's the end of the talk. Yeah, thanks for your listening.
Thanks, Xianyuan Yu-Qing, for covering this paper. So we this paper appeared in one of the post remarks of the of the lectures. So
yeah,
I have a question for you regarding because even in the UCB VI, right? So we've talked about applying the Hoftings and you get slightly suboptimal bound, and when you replace that with Bernstein's inequality, with a careful calculation of the variance using the law of total variance, then you can already get rid of that additional factor of square root of H. And of course, because the setting is slightly different, and we are now we assume that the reward every step is bounded by 1 rather than 1 over H. So you get some superficial dependence on H in the bound. But I thought the contribution of this paper is to improve the high order term, improve that S square A in the regret, so that it's completely independent to H. Could you comment on this observation? So is that where this recursive self-bounding type of technique is really helping? Because neither the monotonicity nor the Bernstein trick were new in this paper.
Yes, but actually, I mean, when I was going through this paper, I feel like the S²A term is it actually comes from two components. So the first component is the 1 over it's a summation of 1 over the frequencies, the 1 over n h case, and second is actually the residue of the total variance bound is by the recursion. But well, as far as I'm concerned, I actually did not realize that even from the UCBVI, we could also get rid of the square root h dependence.
Yeah, it's presented in the original paper, right? The optimal bound is presented in the original paper by Azar et al. 2017, which you put in your slides. And in their results, they assume that the total reward is bounded by h, and then they got a square root of h dependence, right? So if you add the rescaling at this rescaling factor, and you'll get rid of that factor, and you will get the leading factor to be exactly the same as the one that's presented in this paper, right? So the real contribution of this paper is to completely eliminate the dependence on h in the polynomial factor, and show that in terms of h, there are really no difference, like almost no difference, besides the logarithmic factor between the bandits and reinforcement learning. Yeah, and another thing that I observed is that you said that in this paper, they assume that the individual step reward is bounded by 1 over h. Yeah,
oh, actually, it is not.
Yeah, I think it's the total reward being bounded by 1.
The total reward is bounded. Yeah, actually, yeah, that's the case.
Okay, so which is more flexible setting that covers things like a sequential game, right? So you play chess with your friend for many rounds, and the number of rounds is h, and at the end of the day, like whoever wins get a reward of 1. In all other cases, do not receive anything in the intermediate steps, right? So this is one of the cases when you when say in the text generation example, right? Only after you generate the entire sentence will again be used to evaluate your generated tests against some ground truth or some realistically chosen text to tell how much difference there is, right? And in the intermediate step, you don't receive any feedback, any kind of feedback, right? And
yeah,
I think in this situation, the assumption that the summation of the reward being bounded rather than individual reward being bounded by some small value like makes more sense.
Yeah, that's right. I think we have the 1 over h here as to say that we rescale the previous problem setting of the finite horizon MDPs.
Right.
Yeah, so I just want to follow up the Yu-Xiang's comment. So I really, also want to know. So how do they completely get over with the higher order dependence of h? So is this really the due to the this self bounding?
Yeah, I think
procedure?
So.
Okay,
okay. That's really the only thing that's new, and the only thing that we didn't actually cover in the class, and I think it's very interesting.
Okay. Yeah, thanks.
All right. Yeah, thank you very much for coming and for your active contribution to this course, and I'm so proud of all of your the project and how much that you have learned. So you've demonstrated strong expertise in understanding like very technical machine learning papers now. And I hope the materials that we covered in this course will help you not only if you are going to start a research direction in reinforcement learning or applying reinforcement learning elsewhere, but like you now have the expertise and some sufficient training in understanding statistical machine learning literature in general. And you're able to use things like Hofstad's inequality, Bernstein's inequality, martingales, and uniform concentration, and so on, all these fundamental hammers to tackle your problems with a more theoretical flavor. And yeah, so we'll stay in touch. And then if you have any questions regarding the course and regarding things that you don't quite understand regarding collaborations and so on, just reach out, and I'll be happy to talk to each one of you guys separately.